Apache Solar, like I mentioned, is the popular, blazing fast, open source search, enterprise search platform built on Apache Lucene. Lucene, sounds like almost everyone in here is familiar with Solr, so I won't dig into this too much. Lucene is a core Java library. It's an Apache project. Apache Solar is part of the Lucene project. And so basically Lucene and Solr committers release new releases, and Lucene and Solr release together. And Solr extends the core Java library of Lucene and exposes out a real search server that you can use to power search capabilities within your organization. So some of the capabilities provided by Apache Solar, in no particular order, include multilingual keyword search. You type keywords in the search box, get results. Relevancy ranking of results. If I search through 1 million results, I want to see the top 1 or the top 5 or the top 10 at the beginning of my results. Faceting and analytics, which allows you to do very fast aggregations effectively. I run a search, like in this example here where I've got a search screen, the stuff on the left where you see, what are the top categories, what are the top counts, what are the price ranges, those are all facets. You can also turn these into things like pie charts and bar graphs, or really any sort of visualization around analytics. And that can be, these things can come back in milliseconds on a keyword search across billions of documents. So it's a really lightning fast, real-time analytics engine. It also supports highlighting, returning back snippets of text that were matched, spelling corrections, autocomplete and type ahead, sorting of results, grouping of results, deduplication of results. It's packaged in a distributed, fault-tolerant, and scalable platform. So you can spin up multiple Solr nodes. You can have a cluster of 2, 3, 4, or hundreds of Solr nodes, and all of the processing happens in parallel. And if any particular node goes down, the rest of the cluster is fault-tolerant and resilient. There's geospatial searching capabilities. We can do radiuses, lat, long, search on different shapes and objects. Complex function queries, the ability to do content-based recommendations. So given a document, find the interesting terms in that document and find other documents like it. Graph queries and traversals, which I'll talk about in just a little bit. The ability to run SQL queries. The ability to do streaming aggregations, which I'll spend time on in a bit as well, to do really interesting computations. Batch and stream processing, a very extensible plugin model, learning to rank capabilities for really top-notch relevancy, the ability to build machine learning models, and many other things, which I spent way too long on this slide already. But Solr is a very powerful open source search engine that you can definitely leverage to do some really amazing things. Solr, as a result, is in 90% of the Fortune 500. They leverage it to power their search applications. I guarantee you that probably 1, 2, maybe a dozen companies that you use every day, whose websites you go to every day, are powered based on Solr. And Fusion is a platform which extends Solr and provides a lot of additional capabilities. So, when I look at Lucidworks Fusion, this is the welcome screen. Fusion is really about extending Solr to be able to pull all of your data into one place. Whereas Solr is a core search engine, you have to be able to take your data and push it into Solr. It takes a lot of time to build connectors to pull data from every data source you might have within your organization. So with Fusion, we've got over 50 connectors to be able to pull data from Google Drive, Box, Hadoop, any place you have data, we probably have a connector to be able to pull it. We also have a robust parsing framework. So no matter what format the data is in, what kind of file it is, what system it's in, we can pull it in, parse it, and turn it into the appropriate representation to go into the search engine. There's an admin user interface to be able to just do point-and-click configuration of everything within Fusion, as well as enterprise-level security, so you don't have to worry about your data, just sitting in this open-source search engine without really tight security that models your domain. We also have experience management. So if you look at what you would want to do when you're building a search application, we all love the command line, we all use the command line, but there's some things that it's just easier to do in a user interface, at least when you're building it out initially. So we have the ability to do point-and-click relevancy tuning, to do machine learning and actually build relevance models that you can load into the system, And we have this concept of pipelines for indexing documents, as well as sending queries into the search engine. So instead of having to install Apache Solar and write a bunch of code to format your queries and your query parameters like you want them to go into Solr, instead you can set up a pipeline and say, well, the first thing I want to do is I want to add a facet stage. Then I want to add a highlighting stage. Then I want to do some relevancy boosting. Then I want to invoke a machine learning model. Then I want to execute my search. And after I execute my search, if I get no results, I then want to go and change a few things and execute another search. And then finally, I return the results at the end. So Fusion provides you with this ability to build these pipelines to be able to effectively build your search application without having to write code. At least if you need to write code, you don't have to write much of it, and you can do it inside of Fusion. We also ship with the Search UI, so in minutes you can have a Search UI up and running, and I'll show you an example and just a little bit about our Search UI that ships with Fusion. One of the other benefits of Fusion is operational simplicity. So if you think, I don't know how many of you guys have worked on search systems before, but what typically happens when somebody downloads something like Solr or Elasticsearch, you download it, you start putting some data in it, you get some interesting insights, and then you need to go into production. Well, what does it mean to go into production? Well, you have to set up clusters, have fault tolerance. If I need to be able to run machine learning, I maybe go over here and do that in Spark or in Hadoop. I now need to be able to pull my data in from other sources. You end up writing a lot of code and a lot of glue just to make the app run. So whereas you should really be focused on your business expertise and your specific domain, a lot of companies spend 90% of their time just setting up this initial infrastructure before they ever deliver any value. So what Fusion does is it takes that infrastructure that you would set up and that you would build yourself, and we give that to you out of the box. So this includes Apache Solar, which is our core information retrieval engine, Apache Spark to do batch processing, to do training of machine learning models, to do, you guys all use Spark, right? Who in here has used Spark or uses Spark actively? Yeah, about at least half the room. So you guys know, Spark's one of the leading open source projects out there. It's really powerful. It comes out of the box with Fusion, and it's backed by Solr. So for those of you who are familiar with Spark, we have a project called the Spark Solar project, which effectively allows Solr to serve as an RDD, an RDD for Spark, so Spark can read data out of Solr, process it, and stick it right back in Solr. And you get the benefits of Solr in terms of very fast retrieval and searching and filtering and all of those capabilities, while still being able to leverage Spark for what it's good at. So we package all of that out of the box, as well as Apache Zookeeper for cluster, being able to manage fault tolerance within the cluster. We also have a bunch of value-add capabilities like enterprise-level security and pipelines, doing things like natural language processing, recommenders, blob storage, scheduling, alerting, batch processing, pulling data in from external systems. And we expose all of this through a REST API, which has an admin interface wrapping it, as well as an end-user facing UI. So out of the box, you get the entire search ecosystem that your company would use to build apps, so that from day one, you can be focusing on your domain expertise and delivering value instead of spending months and months, and in the case of a large organization, sometimes over a year, just building out this plumbing to begin with. So as one example, Infoblox leveraged Fusion. They put it in place, and their quote to us was, with Fusion's out-of-the-box capabilities, we skipped months in our dev cycle so we could focus our team on where they would have the most impact. So it was basically a 75% decrease in development time for them to be able to get something out of the door and deliver value. Other things in Fusion, and I'm going to get through the sales pitch in just a minute, I promise, but I want you guys to understand the capabilities here because I'm going to be showing some demos in a little bit. I want you guys to have context for it. So Fusion has seamless integration with your entire search and analytics platform. It exposes all capabilities through secured APIs. It provides end-to-end security and, like I mentioned earlier, a distributed fault-tolerant scaling capability and supervision of the entire search application. And operations around Solr, Spark, all these kind of things are really important if you're running something like this in-house. So we provide dashboards and capabilities around operationalizing this. We've got tons of customers, some of the best and brightest companies in the world who are using Fusion to power their search applications. We're really proud of that. And then because this talk is about the Solr ecosystem, and Fusion is part of that ecosystem, I wanted to just kind of differentiate for you guys what you get with Solr out of the box, which is part of Fusion, and what sort of Fusion adds on top of it. So out of the box, you get things like an open core. The core of almost everything in Fusion, from Spark to Solr to Zookeeper, they're all open source technologies, which means you can get in there and you can play with them, you can change them. It's not a black box, which is really, really beneficial, because you don't want to be working on an engine that is just a black box where you just have to basically trust Lucidworks or trust company X to be able to help you deliver on your domain needs. You want to be able to rely on the fact that you can get in there and make changes when needed. So there's an open core. You've got things like faceting, full text search, scalability, real-time indexing, an extensible plugin architecture, extensible plugin architecture, and basic security, all out of the box with Solr. And then the things Fusion adds on top of that are ETL and index pipelines, advanced security, recommenders, the ability to capture signals as users are interacting with the system to be able to better understand user behavior and affect relevancy. Alerts, an admin UI, natural language processing, a web crawler, over 60 connectors, an end user UI framework, machine learning, and support for various big data frameworks. All right, sales pitch over. Let's dive into the core of this talk. What does Apache Solar and the ecosystem around Solr really provide you from a data science standpoint, from a smart data standpoint? So before I can dive into that, I really quickly want to talk about the core of how a search engine works for the half to a third of the room who may not be as familiar with this. So how does basic keyword search in a search engine? Why is a search engine special? Why am I not just using some other data system or database? So at the core of a search engine is this idea of an inverted index. An inverted index, if you look over here on the left, this is what's typically called a forward index. And this is what you would have in a database, in a SQL database, for example. So I've got a document, I've got 5 documents over here, and then they each have a content field that's full of sentences. I could take these sentences and split them apart into terms and have this forward index, where document 1 maps to the keywords once, upon, a, time, in a land far, far away. But what an inverted index does is it flips that in the reverse. So the goal of a search engine, remember, typically is to be able to take queries and very quickly resolve them and then rank the results. And to do that, we can't be doing a lot of computation at query time. So instead, we pre-index all of the searches somebody could possibly run. So for example, my inverted index over here, I've taken those terms, and now I have, think of it as a giant hash table basically, but it's an inverted index, where every keyword that existed in the content is now mapped to the documents that it was found within. And so if I want to, for example, run a search for the word cat, all I have to do is look up cat in the inverted index, and I immediately have every document it's found within. So there's no processing happening at all, it's a direct lookup. Once I've done that, the question is, how do I run a keyword search? So here's an example where I'm hitting Solr, and I'm saying, all right, I want to search for Apache Solar. That's my phrase, or those are my keywords. And all I have to do for that is look up Apache, get the set of documents that Apache's found within, look up Solr, get the set of documents that Solr's found within, do an intersection, and then I've got all the documents that match the keywords Apache and Solr. If I wanted this to be a phrase query, I would do the same thing, and then I would leverage the position in which the terms are found within the index. That's the core of how a search engine works. You do a direct lookup, you do set intersections if I'm doing keyword A and keyword B. I do an intersection if I'm doing keyword A or keyword B. I do a union of the sets, and any other complex Boolean logic you can imagine just doing set operations to resolve the query. So that's all well and good. The question is, how do I go from having a content field like this, where it's just a bunch of text, to having an inverted index? The naive thing to do would be, hey, let's just split on space, and let's, every time I see a space, that's a new word. But in reality, language is a lot more complex than that. And so one of the things you get out of the box with Lucene-based search engines like Apache Solar is really rich text analysis chain. And so in Solr, There's basically, for every field that you would index into Solr with content in it, you can set up an analysis chain that can be composed of three things. Car filters, a tokenizer, and token filters. So car filters are optional, but they basically allow you to take the input text, modify it before it goes into your tokenizer, before it gets split up. So for example, maybe you've got some HTML coming in, and you just want to strip all of that out before you start breaking text apart. That's what you would do that with a car filter. Once you've run through the car filters, you hit a tokenizer. And the tokenizer is what decides how to split your text up. It can either be based upon white space, it can be based upon any non-alphanumeric character, it can be based upon, I've got pipes. My text is all pipe delimited and I only want to split on pipes. You can configure that with the tokenizer class. In this case up here, I've got some text coming in. This is from Solr in Action, my book, which, by the way, I think I have 2 copies of.
They're on the bottom of the box.
What's that? In the bottom?
Yeah.
So I've got 2 copies of Solr in Action, by the way, for those in here. I'm going to give out throughout the course of the night, as well as a bunch of other swag in here. So maybe for folks who ask questions along the way, you'll get something from the box.
Yep.
And if there's any left over at the end, then I'll give the rest out. So this example is from Solr in Action. We've got a tweet up here at the top. Yum, drinking a latte at Cafe Greco in San Francisco's historic North Beach, yada, yada, yada. I take that, I pass that into my analyzer. I am doing a character replace car filter, or pattern replace car filter, excuse me. I run through the white space tokenizer, and then out of that I get a list of tokens that can be indexed into the inverted index. Once I've got that list of tokens, however, I might want to do some additional modification of those tokens. And so that's where token filters come in. And token filters allow you to go through a pipeline of filters which can modify, delete, or add tokens, change the position around. Ultimately, in this case, I've got 5 token filters in here. A word delimiter filter, a stop word filter, a lowercase filter, a remove accents filter, and a stemmer. And throughout the course of going through each of those pipeline stages, I remove stop words like whatever these red boxes were. They were like and, of, the. I remove the stop words. I lowercase everything. I remove accents. And at the end of the day, I have this list of tokens, which is going to go into my inverted index. One really important thing to know when you're working with the search engine is that you almost always want this analysis to happen exactly the same when you're indexing documents as when you're querying on documents. So every query that comes in that has text within it runs through the same analysis chain to be able to generate tokens. And those tokens have to match what was done on the index side when documents were coming in. So as long as you run through the exact same set of steps when you're putting documents into your index as when you're querying, you'll get matches on those tokens in the index, and that's how a search engine works under the covers to match documents. Yep.
Do you have any kind of caching for like the queries? Like if I search for ABC and someone else again search for ABC.
Sure. So the question was, is there any caching of the queries? If one person searches for ABC and then the next person comes in and searches for ABC, will they get a cached result or will it hit the index again? Yes, so Solr has a set of caches, including a filter cache if someone were to run that query, where as long as the index hasn't changed, if somebody's run that search before, the result will be cached, and then the next person who runs the search will get the same result. If documents go into the index and are committed, such that the index is now changed, then that cache gets invalidated and you have to go back to the index to get a new set of results. Yeah, sure. Can you do me a favor? Can you give out random things for people who ask questions if I say so?
Yep.
Let them have a water bottle.
So we have.
This will be fun.
Yeah. So we have. I have an inventory list.
You have an inventory. Okay.
Yeah, I took inventory. Do you want it?
So yes, queries can be cached. All right, so that's basic text analysis. When you start getting further into NLP and what you would want to do, obviously there's this notion of being able to handle different languages. Solr is really powerful at exposing out lots of multilingual capabilities in a really modular analysis chain configuration. So this is an example of an English analysis chain where, you know, over on the left I've got an English text field where I'm basically, yeah, it's maybe kind of hard to see, but actually, is it possible to dim the lights in the front?
Yes.
That would be potentially helpful.
Yeah, I'm not sure which of these is the right one, so we'll just keep trying.
Probably just the front lights. There we go. That's the last one. That works. Okay. It's probably easier to see now, yeah? Awesome.
Yeah.
Okay. So over here on the left, I've got a standard tokenizer. I'm removing stop words that are English stop words like and, the, of, etc. I lowercase everything. I remove apostrophe s or es, which is my English possessive filter factory. And then I might have a list of protected words, and then finally I run through a stemmer, which takes words like you know, engineers and changes it to engineer, or takes words like
Is it plural to say?
yeah, it can take plurals and map them down to a shorter form, basically. So you're, you know, the last thing you want is to be running a search engine where you know, say there's a job search engine and somebody searches for engineers and they get 50 results, and then they search for engineer and they get 20 results, and they're entirely mutually exclusive. There's actually 60 results. That's an awful experience. You want to make sure that when the word people type in, you're matching variations of that word that mean the same thing. And then over here on the left, I'm just doing a little bit of additional analysis because you can really configure this based upon your domain to do whatever
So is
you
it
want to do.
only for nouns? Does it know noun versus verb, or do you know both?
Yeah, so a stemmer. So there's two concepts in search and natural language processing here. A stemmer is really dumb. It's just an algorithm that, you know, based on a specific language, will, for example, for English, remove s or es or apostrophe s. There's also this notion of a limitizer. And a limitizer, a lemma, is the root form of a word. And so if you, there's some commercial companies out there, Basis Tech, for example, is one that does a really good job, where they actually understand the root form of a word. And so if you plug their technology in, it will map, for example, you know, went will be mapped to go instead of we or when, because yeah, a stemmer might do something dumb like that. Just, you know, take a character off the end.
But there's also its and IPS and IP apostrophe is possessive. That's a lot of mistakes in
Yeah.
done, so it can't analyze that, right? Because when it should be possessive versus subject and verb, IP apostrophes. I see that a lot.
Yeah. So she said that words like it, where it could be it, its, IT apostrophe s, that it has different meanings based upon how it's represented, for sure. Something like a limitizer would do much better with that, but you know, it'd have to be a pretty sophisticated limitizer to really understand the context in which that was used. But yeah, but a stemmer is going to be dumb. It's just going to strip things off.
For some of these
Yep.
filters, like your stop filter, is there a list of these stop words that do you maintain that? Or
Yeah.
what
So
happens?
the question is, for the stop filter, is there a list of stop words, and do you maintain that? Yes. So if you see my stop words references stopwords_en.txt, that's a file that you would put in Solr, where you would put in whatever stop words you want, and any time you see those stop words, it removes them from the index. Similarly, the protected words file, if you see the protected words, if any of those come in as tokens, they get left alone by the stemmer because you're basically overriding the stemmer in that case. Same thing if you have like a synonyms file, you would maintain that list yourself. You can generate these things. So one easy way to generate a stop words list is to query Solr, do a facet on all of the keywords that are in your index, and the top keywords that are going to come back are going to be a, the, of, and, in. You know, go down about 15 words before you start seeing something really useful. You can basically take all of those words and throw them in a stop words list because you never want to see them. Yeah, there's some pros and cons to removing stop words from the index, which I'm not going to get into necessarily in this talk unless somebody asks me later. But yeah.
What about like a sound X or something that you can use whenever there's a misspelled word or something?
Yeah, so there's a couple of, the question was, what about a sound X or something you can use whenever there's misspelled words? There's a lot of capabilities in Solr. There's a spell checker There's a suggester. There's also the ability to do variations of words based upon sound or based upon I don't have the full list here. I can look it up for you, but there's lots of different filters to do all kinds of things like that. Many of them including what's that?
I was thinking about other languages than English.
Other languages besides English. Yeah, it gets really complicated when you get into other languages.
But these are all out of the box filters. You don't have to go and create your own.
Yep. All these exist in Solr out of the box, and it's pretty powerful. So one thing I actually see a lot in the data science community. So I'm coming at this talk being someone who's been in the information retrieval field for many years, and we have a lot of really cool capabilities. What I see often in the data science world is for people who come more from a machine learning background without an information retrieval knowledge base, they'll often try to re-implement naive versions of this. So for example, if you're working in Spark and you're trying to create a feature vector out of text, what do? Well, you split on white space so you can get all the words as features. Well, why would you do that? Like in something like Lucene and Solr, there's actually built-in capabilities to process things in a language-specific way to understand words and meaning and how you should tokenize things. So, one of the things we did in our Spark Solr project is we actually extended the Solr analysis capability out into Spark. So inside of Spark, you can basically just say, tokenize this text, and it'll just do it for you. And it'll do it in the appropriate language-specific way, as opposed to you going and reinventing the wheel with a bunch of regexes to try to split text up. So part of the reason I wanted to dive into a little bit of this is just to give you a feel for what's out there. Whether you're using Solr directly as a search engine, or whether you're just leveraging it as a library to be able to do other work. Stuff like analysis chains for tokenizing text in various languages exist, and they're really powerful. And I'll take one more question, and then I'm going to stop the questions for a bit.
Is the Solr English Processor Filter Factory, is that like a Java class?
It's a Java class. Yep.
Is there a specific reason you chose Java for this? Or is it legacy?
So the Apache Lucene project is written in Java, and Solr is based on the Apache Lucene project. And they're Java projects. Yeah.
No plans of moving to Scala or anything like that?
You can write Scala on top of it because it's all the JVM, but Solr is not written in Scala, and I doubt it will ever be. Yep. All right, I'm going to keep going. So there was a mention over here of what about other languages? So obviously this works really well for English, and we all in here have a reasonable understanding of English. What about, for example, Arabic? How do I handle that? So here's an example of how you would set up an Arabic analysis chain, where I start with, at the very top, I start with a standard tokenize filter, I lowercase everything to a stop filter, do an Arabic normalization filter, and then an Arabic stem filter. That was pretty straightforward. Romanian, you don't have to change much for Romanian, but there is a stop words list there. For Persian, there's a Persian character filter because you need to actually modify some of the text before it goes in. You go down a few, there's an Arabic normalization filter factory, a Persian normalization filter factory. You want to run both of them, and that's how you would set up a Persian analysis chain. By the way, these examples all come from my book, Solr in Action. There's like 32 different language configurations we included in there in an appendix. So if you want to set some of this stuff up to be able to handle multiple languages and analyze them appropriately, you can check it out. Here's Japanese. Japanese, I've got a base form filter factory, a parts of speech filter factory, a Chinese, Japanese, Korean width filter factory, Japanese katakana stem filter factory. You can move these things around, but this is a recommended configuration. But if you're an expert in the language, by all means, change it away. But all these just run as a pipeline, and you run through the data. Yep.
So Solr is going to work with different languages at the same time?
Yeah, so the question was, hey, will this work with different languages at the same time? So if you have like a multilingual document, for example. What I'm showing you here is configuration of a field. So in this case, all of these things would be configured as separate field types in the engine. I have another talk that I've given. If you ask me afterwards, I can point you to a link to it, where I talk about how to actually handle multiple languages within a single field. In Solr in Action, chapter, gosh, I can't even remember now. Whatever chapter is the multi-language chapter. I actually have some code there that shows you exactly how you can run these different analyzers and put everything into one field. What someone typically would do with the search engine, though, is have separate fields for each language and put the content for that field, for that language in each field, and then search across all of the fields at query time. So when you take your keywords in, you can actually distribute it across each of the analyzers for each of the fields and get matches that way. That's the most common way of doing it, and that works well until you get to handling dozens of languages, at which point it starts getting slow. So there's some optimizations that you can do, but it's definitely possible to search multiple languages at once. Yep.
One quick question. So, I know that there are some things very similar, like these filters and tokenizers in other languages, or for maybe Spark actually, NLP has some of these features. Is there like a whole lot of overlap right now, or where is like Solr compared to like Spark NLP features for tokenizers?
For text analysis, Lucina Solr are far ahead of Spark. Like they've been doing this for years.
Okay.
That's just what they do. Like it's a text search engine, and it's gotten really good at doing this.
So I could probably use this in the front end, and then when I actually have my machine learning algorithm, I can get them an RDB from Spark.
Yep. Yeah, and if you inside the Spark Solr project, we actually have the ability to pull these settings and configs and analyzers from Solr and leverage them inside of Spark as well. So you can actually just use them directly in Spark.
Spark 1.6 or 2.0, when is this?
1.6. Yep. And will be 2.0. Yeah.
Is it called Spark Solar?
It's the Spark Solr project, yeah.
It's the same capability with Splunk or Elasticsearch. It's all based on the same.
Yeah, it's all based on, it's all built into the Lucene project.
Yeah.
The ability to configure it like this, you just do it differently.
No, I understand that. I'm just
Yep.
trying to like see the RDB. If I can set up this pipeline,
Yep.
and then like read it as an RDB from Spark, I'm good, right? Because in the end, all of these are vectors for me.
Sure. Yep. All right, so, and just to get to the point of, hey, how sophisticated is this stuff? This is, 4 different languages, all the different stemmers that exist. So in English, there's multiple different stemmers that exist, depending upon how conservative or how aggressive you want to be at stemming your text. So for example, for Portuguese, there's there's 4 different stemmers you can use based upon whether you want to be really aggressive, or really cautious or really aggressive, and there's everything in between. For French, there's 3 of them. For German, there's 3 of them. I didn't include English because we already went through English, but needless to say, there's not just one way to process each language. If you want to, if you've got an application that's really focused on recall, and you want to match as many documents as could possibly be an answer, then you would want to go very aggressive, because very aggressive is going to find you false positives, but at least you're going to make sure you find everything you're looking for. Versus if you want to have something that's highly precise, but you're okay if you're missing some results, then you would go with something that is less aggressive, so you're going to make sure you only match exactly what you're looking for, but you might miss some results. So there's a lot of ways that this stuff can be configured. And just to give you a feel in English, I've got a list of original terms over here on the left, like the word country, countries, dogs, runs, running, and then I show you what each of these stemmers does over here. The Porter stemmer, which is the second column, is the most aggressive of these. The K stemmer is somewhere in the middle, and the English minimal stem filter is the least aggressive. So you can see, for example, the word country becomes C-O-U-N-T-R-I in Porter. It's left alone in K stem and left alone in English. You can kind of go from there. Some of the interesting ones I've highlighted with the colors. So association, with the very aggressive Porter stemmer, you get associ. Also the word associates stems to associ. So if you search for association, you're also going to match associates. Whereas at K stemmer and the English minimal stem, leave them alone as separate terms, so they're not going to match each other. Another one that's interesting, the greening here, organizations, organize, and organic, which are all different words with different meanings, all map to the word organ, which is yet another word with a different meaning, if you go with the Porter stem. So it's very aggressive, and you're going to get false positives. You're going to, when you search for an organ donor, you're going to get an organic something donor. which is not at all what you meant. Whereas if you look at the kstem or English minimal stem filter, you're going to get some different results there. So again, depending upon how aggressive you want to be or how cautious you want to be, how conservative, these you can kind of choose your stemmer accordingly for your application. And then of course, like you saw there, stemming doesn't always work. Sometimes you get really weird results. So you might want to be aggressive, but there's these couple of results that just look really bad. In Solr, you have the ability to override this with a stemmer override or a keyword marker, which the keyword marker will protect the list of terms you specify, whereas the stemmer override will apply a list of custom mappings you specify. So you basically with the stemmer override, you say, anytime I see this word, map it to this other word, whereas the keyword marker will say, anytime I see this word, leave it alone.
So this happens after?
So if you think of this going back, an analyzer is a chain that's composed of that car filter, a tokenizer, and a list of token filters. All of these language capabilities are applied as token filters. So you start with an initial token filter, for example, organic. It comes in as my token. I run it through a stemmer, and out of that stemmer comes organ, or organic, or something else. And so...
so if I work for a BlackBerry, I just want to make sure that that is not stem.
Exactly. So what you would do is you would apply this, probably the stemmer override of the keyword marker. You would put that token filter above the stemmer in your chain, so that when it gets to the stemmer, it knows to leave it alone. It marks it. All right, so that's as deep as I'm planning on getting into text analysis, but it's one of the really crucial capabilities, one of the key things that a search engine provides, and that allows you to generate an inverted index to run your keyword searches on, where the keywords you're searching are matching what, more or less the meaning of what you're trying to search in the index. So that's a key thing to understand about the search engine. Yep. Sorry, go ahead.
Index the real-time data set.
How can you index real-time data? Can you elaborate on the question?
Right now, we have a Spark streaming setup. The data is coming for every 2 minutes, so I want to index the data set to search Solr as a front end.
Okay.
Yeah, how to index.
So the question is, how can you index data in real time?
Yeah.
So Solr supports a couple of different modes of indexing. You can do, there's fundamentally this notion of a commit. So you can send 100 documents in and then send a commit, and then when the commit goes in, those 100 documents become visible.
So all the documents are again at this index. Okay. You are indexing all the documents again and again?
Yeah.
Every 2 minutes we are getting the documents. Like if we have 100 documents, every 2 minutes 10 documents are added into those data set. So if you are indexing it, all the 110 documents are indexed or only 10 documents? The recent documents are indexed.
So yes, all right. So the question effectively is about how indexing works in Solr. The answer to the question is you send documents into Solr and you issue a commit. What that does is it creates a sort of version of the index, and you have this thing in Solr called a searcher. And the searcher searches on that view, that version of the index. In the meantime, you can add more documents. Somebody who's running a search is still going to see that first list of documents as you're adding new documents until you issue a commit. And once you issue the commit, then a new searcher is going to be created across both the old set of documents and the new set of documents. Fundamentally, Lucene and its index structure has this notion of an incremental index. What that means is that you never go back and modify old index files. You just, when I get new documents in, I write a new index file, and then when I do a commit, I make the searcher search across all of those index files. And then I add some more documents, and then I search across more index files. And you keep doing that until such point that you've got too many files. And there's something in there called a merge policy, which will at some point go back and rewrite all those segments into a new segment and get rid of the segments. And then it'll start adding more incremental index pieces on top of that new index. But to answer your question, when a commit happens, that's when documents become visible. However, it is possible to do soft commits or even to make those commits happen near real time. So as documents are coming in, the commits are happening so quickly that I see them effective almost immediately. So if you have a real-time application or a need for near real-time indexing, then you can turn that on. Or if you have more of a batch focused application, it's better to just do the commit at the end so you're not doing that extra processing.
Like indexing is slow for a terabyte of data sets. It is really slow. It is taking 4 to 5 hours in a 16-node cluster.
Okay.
So why it is slow?
This is with Solr?
Yeah. So for a terabyte data set.
Come ask me at the break or after, and I can dive into that with you. It sounds a little application specific, but I'd be happy to dive in with you. All right, so that's text analysis. Once you've got your documents in the index, you've got the analysis, you've got each of your terms in the inverted index, and you've matched. I have a search that comes in, and for Apache Solar, like we talked about earlier, I get the word Apache, I get the word Solar, get those sets into the intersection. Then what do you need to do? You're not just going to return all million results that came back. What you need to do is work on relevancy. So relevancy is core to what a search engine is. It allows you to score the results very quickly. You can store millions and millions or billions of documents even and return them back in sorted order. So those of you who have worked with Solr, as of Solr 6, it's switched to using BM25 as the default relevancy algorithm, but the classic Lucene relevancy algorithm is listed right here. Anyone in this room know this algorithm or can tell me what it means, or what it is?
Let me give it a shot.
Go for it. Tell me the main pieces. What are the critical pieces of this?
One piece is statistical correction. So some terms are very frequent, some terms are very infrequent. So there's a TF term in there to counterweight the frequency of terms.
Okay.
The TF and the IDF, those are both the same function there. Boosting is just a sort of custom ability to tweak some knobs. Don't remember what the normalization is. The coordination factor is the number of hits, right? So if you're searching for 5 terms and a document hits on all 5 of them, you have a very high coordination factor. If it only hits on 1 of them, it's a very low coordination factor.
Okay. You've gotten the main stuff. That's good.
Yeah.
Thanks. So fundamental to the algorithm is sum for each term in the query. The term frequency for the term in the document times the inverse document frequency, and then all that other stuff is, we'll skip it for now. You guys know TF-IDF, right? TF is term frequency. It's the number of times a term appears within a document. The inverse document frequency is how rare is that word that it matched. So getting away from the math and just focus on kind of conceptually how this stuff works. Term frequency describes how well a term describes a document. So it's measured by how often a term occurs per document. So if I've got a document with 100 words and it has the word Obama in it, and I have another document with 100 words and it has the word Obama in it 10 times, which one is probably more likely to be about Obama? The one that has it 10 times, because it's just statistically it seems to be more about Obama. Inverse document frequency. If someone comes to my search engine and searches for this phrase, I want an experienced Solr development team lead. How happy would that person be if all the results that came up at the top were the ones that best matched the word "an"? Whichever document had the word "an" in it the most. How happy would that person be? Not very happy. Why?
It's a stop word.
It's a stop word. Okay. Well, what about experienced? No? Why not?
It's rare.
It's too general. It's common. That's why. So which word in this search is the most important? Solr. So I want to rank Solr the highest, followed by probably lead, then by team, then development or experience. So the idea of IDF is the more rare the word is, the more specific it is, the more weight it gets in the search engine. And if you think of the search engine in terms of how it works, I send a query to the search engine, it looks it up in that inverted index, it does whatever set intersections are necessary to get a document set, then it ranks that document set. For the query, and every document, it runs the relevancy algorithm, which is doing, for each term, what's the term frequency, multiplied by its inverse document frequency, and it's effectively doing kind of a cosine. Think of the query as a vector of terms, and the document as a vector of terms. This is the cosine similarity calculation that is being run to compare the document and the query. Yep?
Almost cosine.
Almost cosine. Almost.
And there's an interesting explanation about why they couldn't make it.
Yes. Okay. Good point. Good point. It is approximation of cosine for performance and various other reasons. Good.
Yeah, cosine, yeah, vectors. I might talk a little bit about, for those that don't know term vectors, the term,
Okay.
yeah.
I will come back to that in a bit.
Yeah.
Talk about semi-linear algebra stuff.
Yeah.
If all that was over your head, it's fine. We'll, ask me about it at the break. But that's how a search engine does relevancy scoring. Based upon just keyword matches.
Career builder built on top of.
Sorry?
Career builder
Career builder? What about it?
was it built on top of the Solr?
Yeah, so my last job was at Career Builder, and their search platform is built on Apache Solar, for sure. Yep. As well as a significant portion of the websites you go to and run searches. Yep.
Do you once you do the stemming, like the documents are not stemmed or parsed, right? When you put them in the index, and the documents don't change, right? Like I'm just trying to see if I can intercept the stemmed and lemmatized version of that document, because that's important for whatever reason. Is it possible to just run these filters and just like save the whole document as stem or the stemmed version of that document?
Yeah, you just run through you create an analyzer, put your tokenizer and filters in it, and then put the document in and take whatever comes out the other end, and yeah, for sure. You wanted to break this apart and use it as a tool. Yeah, for sure. You can. They're just Java classes. You can get in there and do what you want.
Sorry, Vish, I can't give you another one.
Okay, so all of that's great, and we talked about TF-IDF, how does keyword scoring work, and that sounds really cool, except for it's not. Meaning, if you don't know anything about your domain, and you just got to have a bunch of text and you just want to run searches against it, fine, use TF-IDF and match. But what about domain-specific knowledge? Almost every search engine you build is going to have some domain. So, for example, a news search website. Things that are more important than TF-IDF might include things like popularity and freshness. I've got a news article. I don't want to show the article that matches this word the best. What I want to show is the article that is the newest, or that's the newest and a lot of people really like it and are reading it or giving it thumbs up. For a restaurant, I really care about the geographical proximity. If I search for Mexican and it recommends me a restaurant in San Francisco tonight, I'm not going to be happy because I'm not in San Francisco. The number one thing I need to know is where's a Mexican restaurant close to me. Also, price range might be important. For e-commerce, likelihood of purchase is probably very important if you can figure that out. For a movie search, more popular titles. A lot of movies actually have the same title for some odd reason. You probably want the popular one or the one that's in the theater now. If I search for Star Wars, I probably want Rogue One if I'm searching right now on a movie website, not an older version. So, popular titles are more important. For job search, things like the category the job is within, the salary range, and geographical proximity matter. If you recommend a job to me where I'm making $10,000 a year, I'm probably not going to take it. But if you recommend me a job where I'm making $2 million a year, I'm probably not going to waste my time because I don't think I would get that job. Maybe one day. TF-IDF can't hold its own against good domain-specific relevance factors.
Where is the document relationship come in when you have multiple documents? Right? So the search happens on one document, but there are sort of other documents that are related to the same document. Right? Is there a situation that you come across?
Can you ask the question again?
All right, my context is email, right?
Okay.
And each email back and forth, each one is stored as a separate documents for us, right? So the search of a particular word brings out this email, that's great. But the whole chain of emails makes the context for us, right? So right now we do things outside of these tools, and then we go grab it, we have our own database. Is there a situation to say that, okay, because you had a hit on this particular document, the sequence of chain of events within that document, other related documents is
Okay, got it. So the question is, the context is email, and the question is, can you take context of other documents into account when you're doing your scoring? So he's got an email that's searched on, but it's relevant because of the context of other emails that were associated with it. The short answer is, I could probably think of a way to do that, but I would need a few minutes to think about it. The short answer is typically a document is going to be scored independently. You can do things in Solr that leverage functions as part of the scoring. And actually, in 2 slides, I'm going to have an example of that.
There are companies in
Yep.
this room that do exactly that.
Yep.
So you can raise your hand and you can find these people back here.
Yeah.
So yeah, if that's your problem, there are companies in here that can solve it.
Okay, go talk to them. I could figure it out for you, but there's.
Yeah, we
Do you have an answer
in LPU
that you can
search.
share?
I need to know more about what he
Yeah.
defines a context as.
Sure, sure. I mean, you can take them all and index them as one document and use that, or you could use Spark or something like it, or Fusion, and process that as a batch of documents, and then for particular keywords and phrases, you could add them to the other documents with a boost, so that when those documents are hit, they come up higher because of the context they were within. Usually, you would do some sort of offline processing to augment the documents to make them represent more relevance for that thing, but there's other ways to do it too. It's doable, but you wouldn't get out of the box, because out of the box, Solr is going to just think of each document as independent and treat it that way. You would have to craft it that way.
Can you group tokens, or is it Tokenizer on a word by word basis?
Can you group tokens, or is it Tokenizer by Tokenizer on a word basis? What do you mean by group
Can
tokens?
you have more than one word in it? Let's say they're words that are commonly searched, like star and wars.
Yeah.
Like an example. Can you look for
Phrases?
yes?
Yeah. So the question is, can you look for phrases like star and wars are commonly found together? How do you handle that? There's a couple ways to handle that. One is in your documents, you can index bigrams if you wanted to, which is one of your token filters can actually take each unigram, each single token, and combine it together with the token before it and the term after it. And then you could actually index the bigrams and then search on those. That tends to work pretty well for getting phrase matches. Also, when you search the index, even though the terms are indexed as single unigram terms, you can actually do phrase searches as part of your query. And so you basically, you could search for the phrase Star Wars and match star and wars and then find them together without having indexes as a bigram. You can also, as part of your query parser, there's one in Solr that most people use by default called the Ndcg Query Parser. It allows you to specify that you want to basically search on phrases as well, and you can do it that way. There's a couple of other ways to do it as well. You could have a synonyms file where you actually find multi-word phrases and match those. There's at least a dozen different ways to do it. But yes, the answer is yes, you can. And then I'm going to go a few more minutes. It's 8 o'clock. I'll give you guys a break in a few minutes. But so we talked about domain-specific relevancy. What about user-specific relevancy? So take these people. This is from Solr in Action as well. Say I've got a bunch of people who I've learned something about by them using my website. So this is actually a job search context. So pretend you've got a job search website. I've got John, who lives in Boston. He wants to move to New York or possibly another big city. He's currently a sales manager, but he ultimately wants to move towards business development. If I knew this about John, either from his behavior on my website or from a profile that he posted or from reading his resume or from any source really, I might be able to do some interesting things when I'm running search for him. I've also got a couple of other people listed here, but I'm going to focus on this last one, Jane. So Jane is a nurse educator in Boston seeking between $40,000 and $60,000. What can I do with that information? Well, one thing I could do is if I've got a job search engine, I'm going to turn that information into a query against Solr. So you see my query up here. I'm searching on my jobs index. I want to return the job title, city, state, and salary. And my query is, I want to search on the job title of nurse educator because that's what she that's what she is. And if I match that exactly as a phrase, as both of those words, then I'm going to boost that hit, the TF-IDF of that hit, by a factor of 25. But I'm also going to match nurse educator as two separate words because maybe it's a maybe the words just appeared in a different order, and I'm going to give that a boost of 10. And also, not only is she a nurse educator, but I really need to match where she lives. So if it's Boston and Massachusetts, I'm going to give it a high boost. But if it's at least Massachusetts, it's hopefully close by, rough approximation here, then I'm also going to match, but I'm not going to give it as high of a boost. And finally, I'm going to add some score to my query if I match the salary range she's looking for. So if the salary is between $40,000 and $60,000, then I'm going to return 10 as a boost that I'm going to add into my query. Otherwise, nothing. So you typically think of a search engine as searching on text or maybe some other fields, but this is searching on features, searching on attributes of Jane, and matching those against jobs. And it'd be interesting to see what kind of search results you get from this. So here's the results. This is all just from a really small sample data set included with Solr in action. But notice the first job that came back as a clinical educator in Boston between $40,000 and $60,000. It's actually a nearly perfect match. It says clinical educator instead of nurse educator, but it's like we know that it's close, even though the search engine it's fuzzy, right? It's like search engine fuzzy matching, and it's fuzzy, but actually it's actually a really good match. The second result that came back was nurse educator in Braintree, close by, but not exactly Boston, but close. And it's also between $40,000 and $60,000. And lastly, you have a nurse educator in Brighton, making over $60,000. What's that?
Yeah, over 60,000.
Yeah, I mean, it's not a great match, and it might be too high, meaning she's not qualified, if that's a proxy for qualification. It may not be, but if you think of my query, it was, if I match all these things, I want that to show up at the top, effectively. If I match some of them, I want them to show up in a descending order, roughly based upon these boosts that I applied. And lo and behold, it happened. Yep, question?
Hey Trey, so based on the results you get from that, could you set up a pipeline where maybe that information can be forwarded to a recruiter or even to that candidate himself, making him or her aware that, hey, we found these hits for you? Is that sort of where this process is leading you towards?
Yeah, so the question was...
Rebuild the mindset, right?
Yeah.
Put in my agent, and is that where this is coming from?
Yes, so the question was, could you set up sort of an alert or something where, if these results were matched, you could then send an email automatically to a job seeker? Yeah, you could for sure. And to that point, the next, what have I done here effectively? Like, I'm not doing a text search here. What am I doing? Like
metadata.
What's that?
Metadata.
It's metadata, but like at the end of the day, I took Jane. She put in no text. I just knew things about her, and I automatically matched content to her. What's that called? Recommendations. You just built a recommendation engine. A text-based or a feature-based, content-based recommendation engine, but it's still a recommendation engine.
But what did he use for the semantic? I mean, how did he break that sentence down?
Which sentence? Good question. The sentence here was just my English representation of a profile.
Oh.
So like, imagine this being like field and information in a profile that I've learned about Jane. This was just, it's easier to explain this way. Yeah. Go ahead.
Can you set up domain searches for, like an adjective, say, plaid, and you're looking for another word like shirt within a differential of like 5 words on either side of the word plaid?
Yeah, so the question is, can you basically search for a word like plaid and look for the word shirt within 5 positions left to right? You can. You can do searches with edit distances. There's something called slot factor. Part of the query syntax in Solr is you can basically say, I want this word within 1 or within 5 or within 10. You can think of a phrase query, quote software engineer end quote, as a search for those 2 terms with an edit distance of 0. Like there's no edit distance between them. And then if you add an edit distance of 1, 2, 3, 4, 5, 6, 7, etc., you can search for words close to something but not exactly beside it. Yeah, that's important.
Trey, are you going to talk about the function? So I want to know if you break apart a function, like I know there's a function out there that may have different intentions, undesirable intentions, and we know that it's going at a company, but I know that they break down the function into different participles. So if we know what those are, can we search for those? And then, kind of like with the email, I know that here's the area that it's going for, and I want to look for, if I get 3 out of 5 of these pieces coming in, I want to alert on it.
Yeah, so the question is, can you basically do like a fuzzy match on related terms, something like
Yes.
that? So like, if I don't want to match the exact text I typed in, but I want to match things that are related to it. I'm going to talk in a little bit about how to do that. Yep. I'm going to keep going a few more slides, and then I'll give you guys a break. So yeah, we found results for Jane, and we just built a recommendation engine. So one thing I'm going to do before the break is do a quick demo. So that was effectively a content-based recommendation engine just based upon some attributes. I want to show you really quickly some other kinds of recommendations you can do with Solr. And to do that, I'm going to quickly launch. All right, give me a second. I'll let the demo launch. And while it's launching, I'm going to talk about sort of what I call the relevancy spectrum. So to me, we talked initially about traditional keyword search. How do I do text matching, TF-IDF, and get some results? I don't know anything about the domain, and I don't know anything about the user, but I'm going to match some results out of the box. We also just saw some recommendations, and I'm going to show you a better example in a second using collaborative filtering, which uses behavioral information about how people interact with my documents to be able to let me recommend other documents. And there's also this third area, which I call semantic search, but it's this notion of understanding the domain. When somebody types in long sleeve T-shirt, is that 3 different words, or is that does that mean something together? If someone types in engineer versus software engineer versus senior software engineer, those all actually have somewhat overlapping but largely different meanings. And so how do I understand phrases and within the context they fall within? And also, what are some other related terms and phrases? To the question a second ago, what are other related terms and phrases so that even if my document doesn't contain the thing I searched for, it conceptually does because it included all these other things. So I refer to that as semantic search. And to me, relevancy is a spectrum. And so is search and recommendations. So a lot of times people, especially in the data science world, tend to think of search engines as this thing you put documents into and do text searches on. And if I'm going to get the only way to get a result is by sending a query. And then think of recommendation engines on this other, as a separate system over here, where I'm not going to send it any queries. What I'm going to do instead is just have it automatically generate content for me, recommend items for me based on what I know about the user. But people think of these as 2 separate things. In reality, they're just 2 ends of a spectrum. For example, if I go to a website and let's go back to that restaurant example earlier. If I go to a website and I search for Mexican, does it need to return me random Mexican restaurants or the highest rated Mexican restaurant? No, it needs to return me Mexican restaurants in the city where I'm located. Well, how does it know that? It has to learn something about me, some characteristic about me it knows. If I have in the past gone to very expensive restaurants, then maybe it should recommend me very expensive restaurants. It's still a search engine, but it's a personalized search engine based on what it knows about me. Likewise, if I show somebody a set of recommendations and they see them and they don't like them, they should be able to go in and say, hey, I don't like, I want to increase the price, or I want to adjust this other filter. They're not 2 separate systems. There's really this entire spectrum in between, where both search engines and recommendation engines are just matching engines. And the goal of both is to deliver the most relevant content to the user based upon the information at hand. It might be just a query, in which case I'm recommending based upon text, or it might be, I might know everything I could possibly ever know about this user. Like in the case of, Google, they know enough about you, they can really get right down to exactly what you're looking for, sometimes before you even type it, because it's a spectrum. It's not 2 separate systems. I'm going to show you how to build recommendations leveraging a search engine, which, getting back to the linear algebra stuff earlier, for those of you who are familiar with linear algebra, you can think of that inverted index as a giant sparse matrix where you've got a bunch of terms mapped to documents, and every query that comes in is a vector, where you're doing a vector multiplication against that sparse matrix. And in doing so, you're doing the exact same operation that you would be doing in a recommendation engine, albeit most of the time you would do a matrix by matrix and then generate a list of results offline, but you're doing the same operations. And with the search engine, you can do it in real time. Document updates can be coming in, and for each user, you can generate recommendations on the fly based upon the most recent information you've seen, milliseconds ago. So I'm going to show you an example really quickly before we take a break. So I think I am. There we go. Okay. So this will be my first demonstration of Fusion for you guys.
Extra points for showing the command line.
There we go. Alright. So this is Lucidworks Fusion. And inside of Fusion, we go into the search context. So I have indexed a bunch of data as e-commerce data. So you have millions of products that you would buy at basically like an electronics store, e-commerce store. I'm going to come in here. We've got a couple of different concepts in here which are useful for the demo to know about. We talked earlier about index pipelines, and this is basically how you configure data to flow into the index. We also have query pipelines, which allow you, for example, here, go to my query workbench so you can see what's going on. And just for the sake of readability, let's the name of the product and the description. Let's see. Search for iPad and let's see. Short description, that works. Okay, so now I can actually see the product. So I search for iPad and I see this list of things over here. The way this works, if you're familiar with Solr, or even if you're not, I have a bunch of pipeline stages. The first thing I do when I'm running my query is I set the list of fields I want to query. So in this case, I am going to, sorry, the list of fields I'm going to return. So I'm going to return the category name, class, and all these other fields in the return fields down here. And for field facets, this is me defining these facets over here on the left. So I'm saying I want to facet on the type field, and I want to facet on the department field, and I also have added some range faceting in Solr on the price field, which should be showing up. I'm not sure why it's not. I will check on that in a minute. And then finally, I run my query against Solr. And so what I can actually do is I can enable and disable these things. For example, if I want to turn my faceting off, I just click over here and I disable my facets. It reruns the search, and I can see over here what my search results would look like. So I'm going to go ahead and re-enable those just so they appear there. And then we also have, I told you we have an end user user interface. It's called Lucidworks View. And so here's a list of search results coming back from it. So if I search for iPad here, notice I see the exact same thing that I saw in the other window. And if I were to, for example, disable my facets and save them, save this pipeline, and then come back over to View, all of a sudden I would see no facets over here on the left because I have, well, one second. That's why. No attention to the mail curtain.
What is the framework on which this website was built?
The UI?
Yeah.
So this user interface here is called Lucidworks View. It's an out-of-the-box search user interface that Lucidworks provides.
And is the code for this one open source? Or?
The code for View is actually open source, but it uses Fusion as its backend, and Fusion's
but what is
not open source.
What is the front end for this one?
What do you
like
this is the
Angular
front end or CSS? Or what is the
it's an Angular app.
Angular?
Yep. Yeah, so this is an Angular app here. You know, I'm running searches. Let me search for iPad again. You'll see, hey, my facets are gone now. Whereas if I come back into Fusion and go to my query pipelines, then, sorry. I'm going to come to my query pipelines and I'm going to add them back and save. Now they will show up again. And there they are. So effectively what you can do with Fusion is build the pipelines in the back end and all the business logic and everything that you would normally write tons of code and build your own application for. But you can do it inside of Fusion instead and immediately change and move, and I can even drag and drop and change the way my search results look. So what I wanted to show you here, for the sake of this demo, was recommendations. Take this back really quickly. My plain list of search results again, and let me just search for, so like for example, here's a laptop. I see my laptop. This list of search results here, if I look here, I see some other laptops that are similar, a Dell Inspiron laptop, HP laptop, another Toshiba laptop, etc. This list of results comes back from what's known as collaborative filtering, and to generate this, we basically took our e-commerce index, we took a list of signals that was collected, basically whenever people, normally for an e-commerce company you would look at when people buy a product and use that as a signal of how, if people bought two products together, they're probably likely to be related. In this case we're using click signals, so people who ran searches and clicked on a bunch of different products, they were probably exploring them together and comparing them. So we use in Spark an ALS algorithm, alternating these squares, to be able to generate a matrix, do matrix factorization, and ultimately generate a list of item to item recommendations. So for this item at the top, this is the list of other related items, and we basically generate that in Spark and feed it back into Solr and index it into a collection. So I've got a collection here. I've got a couple of collections that were generated. One is my signals collection, where every time someone takes a click, I store that click back into Fusion. I can also aggregate those signals to be able to leverage them for relevancy boosting. And I also have these item similarities and query item similarities and lots of different ways to do recommendations. I can even do user item, where for particular users, I find a list of recommendations for things that user would like based upon their activity and their behavior. And this is some of the power of what you get with Fusion, where you can take Solr, have people running searches in Solr, index those signals back into Solr, use something like Spark to generate a list of recommendations, save those back into Solr, and then all we have to do at query time is modify our pipelines to leverage those recommendation signals and information and be able to boost search results or show lists of recommendations. And these feedback loops are how we drive really relevant search results.
So this one is a specifically customized one, right? I mean, you took this specific data and said that this product goes with this product, and then who built the model for this one?
It's Fusion. It's all code. The input for this is a bunch of documents, products.
Right.
Sorry, a bunch of products and a bunch of clicks, and that's it. And we run a model in Spark to generate these recommendations, store them back in Fusion, and we can leverage them.
And this comes with Fusion.
So it's the Spark integration. Yes, it's all it comes with Fusion.
So you need to write that Spark application, or it's already built?
It's something that at Lucidworks we've written, and you can leverage it. Yep.
What would the ALS stand for?
ALS is alternating least squares. It's a It's a optimization algorithm.
Is it the low rank matrix factorization? Is that the
Yeah.
the
So
core?
yeah, it basically allows you to solve for. You take what's it? You solve for. You alternate the parameters you're solving for to make the equation easier to solve. And you know, you could also do some sort of gradient descent or something, but it's more complicated. This can be done in a parallelized fashion. It's easier to solve for. It's just an alternate way of doing the collaborative filtering.
The pre-built implementations for the item recommendation and the linear regression Tay-subspace mapping, that's part of Fusion, but not built into Solr itself?
Correct, yeah, so this gets kind of to the distinction I was trying to set up at the beginning between Fusion and Solr. Solr is the core information retrieval engine. It provides you the text analytics, the analyzers, tokenizers, faceting, all those capabilities. But when you're building a search system, you have to build all this other stuff around it. When you want to build a world-class relevant search engine, there's even more stuff you have to build around it, including having Spark or some processing framework, writing these jobs where you can do recommendations and build things from these signals. So Fusion gives you all of that. It's sort of all the stuff that you would have to build in your own domain-specific application, but we provide it in a more generic fashion, and then lets you customize it for your domain. Yep.
I'm just curious question, like, if you have different kind of feeds like XML feed, JSON, and Word, like, how do you save this data? You just read all the feeds and save it like in MongoDB. How do you like read these feeds and save it?
How do we save? The question is, how do we? If we've got.
Do you save this data as one format at the end, or like you just keep it as it is? Like if you have JSON, XML, and Word, and you want to search all these documents.
Yeah.
Yeah,
so the question was, if you've got a ton of data in a lot of different formats, how do you get them all into the search engine and search on them? It feels like a nightmare of a data modeling problem. The answer is in Fusion, we've got this concept of a parser. And the way it works is when JSON comes in, I can show you. An example of what parsers look like. So when data comes in, it runs through this parsing chain. So let's say that I gave Fusion a zip file full of zip files, full of folders with XML, JSON, CSS, and other sort of like nested, nasty archive full of data. How would we handle that? You take that, you pass it to Fusion. The first thing Fusion does is it passes it to the archive parser. Says, hey, is this thing an archive? Yes, it's a zip file. Okay, well let me start extracting and streaming things out of that. And then it takes those extracted things and passes them back into the parser. Says, all right, this first thing I extracted, what is it? Oh, it's another archive. Well, let me extract it and pass it back in. What's this first thing? Oh, that's a folder. Well, what's inside of it? Well, that's a JSON file. Okay, well the next thing I'm going to do is hit my CSV parser. It's not CSV. Next thing I'm going to do is hit my JSON parser. Yes, it's JSON. Parse that as JSON, and then go to the next file. And it just sort of continues in this loop. More or less, we've just configured a really sophisticated pipeline of parsers so that, in theory, anything you throw at it should be able to parse. In practice, it's 90% accurate. I don't know the exact number, but you can come in and twiddle and change the configuration here based upon your data if it doesn't parse correctly. But by and large, out of the box, any data you throw at Fusion, it should handle pretty well. Yep.
And Apache Tika down there will do Word formats and a couple hundred formats. But
yeah, Tika's a nice fallback. If you don't know what to do with your data, you throw it at Tika. It can typically do some good stuff with it. It also does some weird things sometimes. But,
But the eventual data is saved as what format?
It's the eventual data that goes into Solr is you take these documents, you parse them. You take this content, you parse it into documents, pass those documents to Solr, and then you analyze and tokenize everything and index it into Solr. You can store the original content if you want of the fields, or you can just index it. But then what's in Solr, what you're running searches on, doing recommendations on, it's indexed documents in Solr.
How about the pipelines?
What's that?
How about the pipelines? Right, the pipelines we build. Adding to his question, how is that being saved?
How are the pipelines saved? Is the question.
Where is it being saved or?
Okay. Yeah. So for example, if I
what's the format?
if I build a query pipeline like this, this thing, yeah. So everything in Fusion is driven off APIs. So what you see here is effectively an Angular app that's doing AJAX requests back to the APIs. I can even
to edit this in the command line, right?
Yeah, you can do this all in the command line. The UI.
What the file format? Is that the JSON representation?
It's a JSON. Yeah, I'll show you. Let me. I'm gonna do this for 3 more minutes, and then promise you guys I'll give you a break. Network. There we go.
What's the underlying data storage layer actually?
So this pipeline, for example, collection. There we go. Query pipeline. So to give you a feel for. So this is what the pipeline looks like. It's stored in Fusion. You know, it's my configuration for everything you just saw on the screen. It's a Fusion object. You build it, you save it in Fusion. You can export it. You know, email it to your buddy. He can load up Fusion and take the whole app and run it himself. So you can sort of build these transportable apps and build them, save them, check them into GitHub. Someone else can pull them down, run them. It's a way of just building data-driven applications. Leveraging the platform.
And Fusion's got a bunch of you've already got templates built out there for us, right?
Do we have templates built out in Fusion? What do you mean by templates?
I thought I read along you've got templates that you can leverage the products with.
Yeah.
The views.
Yeah, the views, sorry.
The views. Yeah. Yeah, so, I mean, more or less, yes, everything's transportable. We've got a bunch of example demos, like this e-commerce demo,
yep.
Various other things. Just a reminder, Fusion is a paid product, so, I'm happy to talk. We've got a lot of other stuff to talk about too. I'm happy to talk with you guys about Fusion if you're interested in, free trial or demo or what have you. I do want you to understand what it's capable of and what it adds to Solr. So, yep.
So going back to the earlier collaborative filter, right?
Yeah.
So is it from the search side of click streaming or click to capturing of those events? Is it from the same side, or can the data also come from partner organizations like profiling, and like let's say if I'm buying a product from Walmart or
okay.
Amazon.
So the question is, for building the recommendations, these signals that we're collecting, can they only come from clicking on search results, or can they come from elsewhere? The answer is they can come from anywhere. In fact, for this demo, I didn't come and click millions of times on things. I downloaded a bunch of logs and uploaded them into Fusion and ran an aggregation to generate my signals collection. And it's a very flexible format. You could, if you've got Omniture or Google Analytics or something and you want to tie into that, and you can pull from their APIs, write a little bit of code to format them, pass them into the Signals API, then you can leverage them and use them to drive your relevancy. And you can use the Fusion algorithms to generate recommendations and run signal boosting. I've actually got another demo I'll show after the break on signals, just leveraging the signals directly to boost things up and down. I think you'll find it interesting. But the answer is yes, it's very flexible, it's all API driven, and the format is flexible. You can pump data in yourself from wherever.
And I think there was a question about storage medium per se, and I know it stores on Hadoop and it stores on regular disk as well.
Yeah,
the underlying storage.
Yeah, the underlying storage for everything you see in Fusion. Some of our configurations are stored in Zookeeper, but otherwise everything is stored in Solr. So you can use Hadoop for some things in here, but keep in mind with Spark, with Spark using Solr as an RDD, Spark can both pull data out of Solr and store data back into Solr. Solr is a NoSQL database, and so you can leverage it for search, you can leverage it for analytics, you can leverage it for recommendations, but you can also just store objects in it, store blobs in it if you want. And so we store everything in Solr. So let me come back here, and then I think this is a good stopping point, and I think what do you guys recommend for a break?
15 minutes.
No,
only.
I'd say 10. How about 8:40? Till 8:40.
8:40. We'll get started again. All right. Thanks, guys.
Sorry, didn't mean to.
Oh, got it, for View. Yeah. So depending upon where the data came into your application, what format it came in, we detect that in View and can display it different. Like if it's a tweet, it'll be displayed. Yeah. I didn't realize you were talking about semantic, but you're talking about like the back end. Yeah. What time do you think? Do I need to?
Got my hands off the table. It's a lot of So it only seems like one other. It's awesome, man. Good job. You said 7 demos. It's really important.
Oh yeah.
There's so many things I can think of in the last 2
A lot of them come back to
someone doesn't pick it up, the camera will catch it. It's hot. It's a hot bike.
Anyway, just want to make sure that you get what you want to show.
I think I'll just need to take those questions. Yeah, sure.
I didn't see it. I was going to ask about, well, to start with, it's about as well, a lot of,
So yeah, we are kind of using Solr on this as well. And for them we use Oracle. So RDF. So it's not a good marriage over there. It's like you guys doing us. I saw that the RDF, the views are it's possible to do RDF on Solr. We're going to talk about it.
I'm not going to spend long on it, but I'll point you to some code. I mean, I was trying not to talk about there's a lot of questions. Great, it's good. Yeah.
So, basically, every document
Yep.
We start doing, right now, it's doing, so you do a search, okay, you're the person that starts individual words, you're searching for but we started like treating each document itself as a vector and basically, try to map some of the vectors into this vector and try to get that level where, because right now, we're in data, you do a bunch of tokens, right? And you're doing that, and then you have like a formula that basically says to everybody you have a formula that you're still still different documents as like one body, right? That's a question. Have you ever, are you getting to the point where you're actually treating this document as not just like document? You can run that through an LSTM and actually convert it into a vector that is specific to vector.
Yes, I mean not for the purposes of
Gianwan, this is Ron.
I won't keep on this right now. I was just wondering, is it at that level yet? I know that the LSTMs and these things have gotten to the point where they no longer have to like bigrams and trigrams, they only have limited applications. If you do like these LSTMs, you can actually match vectors to vectors, not just have vector matches.
Yeah, so do like document to document. Yeah, so one of the things I'm going to show you is a little bit, so there's a project that actually software that's open source. I'll call this effectively what it does is it allows you to leverage these sort of like underlying actions to be able to relationship with things. There's another project
Solar. This builds the whole range. You can build
That's all part of the
you can build the alloy that is like
so I work on including back on some. So there's right now the same. I know that the same team is not looking at both of them, right? And that's a problem. And I feel like all the so if I have to do like how would that work?
We can. You can download Fusion on your laptop. The recommendations that I'm showing doesn't come with the out-of-the-box.
Because I mean, like, once you do the indexing and putting it into the rest of the stuff is a lot. The query, I gotta ask him. And you do the documentation as much documents like this.
What I was showing you was what we're doing is we're using Spark to do matrix factorization processing, and then taking the output of that and saving it back up in a Solr Fusion, and then leveraging that in search engines. So, like, think of it instead of me generating a matrix of my which we have done.
But those metrics are coming from. I don't have some kind of people who bought this box.
Item by item.
But that is not coming from the document, it's coming from a computer.
It's coming from the signals. The signals are purchase signals. Well, yeah, they're hiring.
Right. So there's two things together, and then we have two things together.
Yeah, so what you can do, so you don't have to do matrix factorization. You could, for example, take every and index it on the original. It just, if you've got a lot of data to be computation, it's feasible and it's not like it. So instead, what you do is you typically take all the signals, you do matrix factorization, and it does two things. One is it reduces the set, two is it allows you to fill in.
So you take like the just take the first couple of BD and CD
yeah, so you do that, and then imagine when I'm running a search for an item. Now it's not just the recommendation for that. The collaborative.
Well, I get so
I might include some keywords. That's what the person is trying to search for. I might include geospatial stuff, and I might include these collaborative features.
We were talking about that earlier. A couple of these things we could.
So, guys, let's do this. Everybody, let's do this. I know there's a long line of people who want to talk to him. So, those people that want to stay late, I think you've got time.
I can stay as late as you guys want.
You can stay late tonight. So let's go ahead and finish the group portion. We've got, just also a reminder, we've got some other goodies in here. We've got the book itself, Trey's book.
I'm going to save these for the end. For people who stay all the way to the end.
Yep. Your last man standing, last person standing.
So we have three or four of each size, XL, large, and medium t-shirts.
Okay.
And we have red
How many of those do we have?
We have 30 webcam blockers.
Yeah, so let me keep going. And I'll put some of the demos right there. You just get those out. There's webcam covers on this middle table for anybody who wants one. You don't need to ask a question, just grab it.
And stickers.
And Solr stickers if you want a Solr sticker. Set them right here.
Thank you.
All right, I'm going to keep going. I'm going to stop taking questions for the next little bit, and then feel free to ask questions. If you got something you have to ask, feel free, but try to hold the questions. All right, so the last thing I talked about was this relevancy spectrum, and the concept of recommendations, traditional keyword search, and semantic search. I just showed you an example of recommendations where whereby users who clicked on this item also clicked on these other items, and how that can be computed in Spark and pulled back into Solr through Fusion. The other thing I want to talk about, just in terms of the sophistication of an app. So most of the things I talked about thus far, if you think about keyword searching, TF-IDF, those all fall at the very bottom of this spectrum of sophistication, as I would call it. We talked about going beyond TF-IDF and using some domain-specific relevancy factors. And that starts moving you further up the spectrum. But there's a lot of things that you're going to want to do along the spectrum, including leveraging taxonomies and entity extraction, maybe building and leveraging ontologies to understand not just text, but what words and phrases mean and how they're interrelated. As you move further up that spectrum, you start talking about things like query intent. So how do I classify queries to know, was this a query asking me a question? Was this a query looking for some documents? Was I looking for an item, etc.? How do I parse that query? The example earlier of engineer versus software engineer versus senior software engineer. How do I parse that correctly so that I'm representing the user's intent? And then, clustering and classification techniques. You keep moving further up that spectrum, and you think of things like relevancy tuning. So how do I take these signals, which we talked about, where people are clicking on things, and leverage those to be able to drive more relevant results in the future based upon what people have clicked on? How do I do A/B testing to figure out which algorithms are outperforming other algorithms? And then there's something I'll show you in a minute called learning to rank, which is built into Solr, which is one of the more modern ways of building relevance models, where you effectively take relevancy judgments about, for this query and this list of results, which ones were the most relevant, and you use those to build a ranking classifier, which, when I run my query, allows me to take different features, tons of features, and to be able to do really sophisticated ranking of results. As with Solr 6.4, which is coming out in about a week, so it's cutting edge stuff. There's a really nice learning to rank module integrated into Solr. I'm going to run through it in a second. Like out of the box, there's some scripts that come with it. It walks you through how to do the whole thing. It's really nice out of the box. That's one of the things I love about Solr. It's an open source community with contributors from organizations all across the world. So the learning to rank module, for example, was built by Bloomberg and contributed back. My company, Lucidworks, may not have ever built that, but they had some really sophisticated search needs and contributed it back. So it's really nice to be in a community where these kind of things are coming back into the core product. And then lastly, on this spectrum, there's this idea of self-learning, which I have at the top. So instead of having engineers go and data scientists manually build all of these things out over years and years, how can we actually have the system potentially be a self-learning system? It does something, a user clicks on results, the system can learn from the user's clicks what worked and what didn't, and adjust and just become more and more intelligent. And not only learning from behavior, but also learning from your content. When content comes in, can it learn relationships between things within the content to automatically generate ontologies and understand relationships between things and be able to do concept expansion and semantic search? How can we do all of these things without a lot of human intervention, where the algorithms are driving what's going on? So I'm going to, as we get further into the talk, for those of you guys who can stay late, I'm going to dive more into some of those concepts as well. Key to this idea of self-learning is what some of us in the industry refer to as reflected intelligence. So what is reflected intelligence? My definition of reflected intelligence is it's leveraging previous data and interactions to improve how new data and interactions should be interpreted. Lucidworks talk about 3 C's related to relevancy here. One being content. So what are the keywords and other features in documents? Collaboration, which is how have others chosen to interact with your system. And the third is context, which is available information about your users and their intent. So how can we leverage content, collaboration, and context to have the system learn how to deliver the most relevant results? We already talked about this some with signals and with recommendations, but it's through this idea of feedback loops, where one of the beautiful things about a search engine is that you have this closed loop system. You can have a closed loop system where a user runs a search, they see a list of results, they take some action on those results, the system learns which actions were good, which actions were bad, and then uses that to modify its models itself to generate results for new user searches, and then it's a virtuous circle where the system can continue learning and getting smarter and smarter and building better and better models, ideally without a human in the loop to drive that necessarily. So some examples of reflected intelligence include one we already saw, which is recommendation algorithms, building user profiles from past searches, clicks, and other actions, identifying correlations between keywords and phrases, building out automatically generated ontologies from content and queries, determining relevancy judgments using things like precision, Ndcg scores, etc. from click logs, learning to rank, which I'll show in just a minute, which is using relevancy judgments and machine learning to train a relevance model, the ability to discover misspellings, synonyms, acronyms, related keywords, etc. Automatically from query logs or from content, disambiguation of keyword phrases with multiple meanings, and ultimately learning what's important from your content. These are all examples of how the search engine can learn, and a lot of this learning can take place by leveraging your query logs, which are a gold mine of information. So I'm going to skip over this section. It's a general overview of relevancy, how you measure relevancy, how you tune it. There's, in search, in information retrieval, Ndcg scores, which is normalized discounted cumulative gain, are one of the better ways to measure search results relevancy. I'm going to kind of skip over what it is exactly, but I do want to jump into learn to rank, which is based upon having some relevancy measure here. So the general idea behind learning to rank, also commonly referred to as machine learned ranking, is to apply a machine learning technique to discover the best combination of features to provide the best ranking for search results. So typically you start with a labeled set of documents. So I've got queries mapped to lists of documents and ratings for each of those documents in terms of how relevant they were. And then you effectively, in a search engine, would typically run your normal search using something like TF-IDF similarity to get say there were 1 million results, I might run TF-IDF to limit that down to 10,000, my top 10,000. And then from that list of top 10,000, I would run a more computationally expensive model, like a ranking classifier built from using learning to rank, to really get into the nitty-gritty details of which features matter and which didn't. So you could use a ranking SVM. There's Lambda Mart, which is using regression trees. RankNet has some boosted trees and neural network implementations of this. A lot of these are open source and you can download them and leverage them, but you basically build a ranking classifier on top of them. Like I mentioned earlier, there's a learning to rank capability that's now built into Solr, as of Solr 6.4, which will come out in about a week or so. And so this is pretty cutting edge stuff. It's been around in the information retrieval world for a long time, but not really integrated into major search engines, certainly not in an open source fashion. So we'll skip over that and just jump into a quick demo. My demo is not sophisticated. I'm not showing you a highly relevant learning to rank implementation. What I'm doing is showing you out of the box how you would go about building a learning to rank algorithm very quickly. So let me. All right. So the first thing I need to do is start Solr. And so learning to rank is a contrib that let me just get a new tab so it's not. So what I'm going to do is I'm going to run, I'm going to start Solr on port 8984 using tech products, which is just an example data set that comes with Solr. And I'm going to explicitly turn the learn to rank module on. It's a contrib module, which means it's not on by default. Let me. Awesome. I think I already started it. Oh, that's what's going on. 1 second. recommendations demo is fighting with ports. Has taken over my port. I need to stop that real quick. Okay, try it again. There we go. Now it's starting up on port 8984, and make sure it's working. Yeah, okay. So first things first, I want to run a query for iPod. So this is in the tech products category. Notice I get a couple of results coming back, and make it a little bit bigger, easier to read. If I were to try to invoke my learning to rank model, which works as a re-ranker, the query syntax to do that, decode. So this is an example of what a query would look like going to Solr using learning to rank. I've got my query of iPod, and RQ stands for re-rank query. So after my initial ranking has happened, I can get my list of results and re-rank up to, looks like I'm re-ranking 25 documents here. So I take my top 25 documents that came back from my TF-IDF scoring, and I use the model called example model, and run that as a ranking classifier to re-rank the documents coming back. I think if I run this now, it's going to give me an error because I haven't built a model yet. Yes, error, cannot find model example model. So I'm going to switch back to the command line, and actually, I'll cheat. I'm going to run this command. So this command ships with Solr. It's called train and upload demo model. I'm going to run it really quickly. Of course, I'm in the wrong directory probably. Train and upload model, pass my config file in. Let me just show you before I do that. So my config going in there basically, so as my host, the collection I'm looking at, just some general configuration for how I'm going to go about training this model. This is all what comes out of the box with Solr. The interesting thing here is you have a features file, which allows you to define features in your documents that are the things you want to rank on. And that's really interesting and a really clever way of implementing this because if I look at example features, I have effectively defined a bunch of features in terms of queries. There's numerous ways to define them, but if you look here, I've got a feature that's called is in stock. And the way it's defined is by searching on the field of in stock. So if I get a match on that field, then the feature has a value of true. Similarly, I've got my original score, price. So some of these features are going to be based upon the query. Some of them are going to be based on the documents. But I've got one here that's really interesting called product name match. So this says that if the query on the field name of the user's, if the user's query matches in the field called name, then that counts as a feature. So not just matching in the text, but also matching in the name field. And so when my re-ranker is running, it takes that document, it takes the query, figures out if there's a match in the name field, and if so, it counts that as a feature. And obviously, if you think just with your gut, matching on the name field is probably going to give you a better result than matching on the text field. So the ranking classifier, when it's being built, is going to learn that, given queries and documents or their rankings, generally speaking, documents that had a match in the name field ranked higher. Therefore, the ranking classifier will learn how to rank these features. and you can model any number of features you want based upon queries or any representation here. The interesting thing is you don't have to go and write code to do all of this. You can literally sit there and think of any possible query that would tell you something interesting about your data, model that as a feature, and then have the ranking classifier learn that feature. Yep. So go ahead.
So can you modify it on the fly and then reapply it?
Yeah, so the question is how dynamic can you make this ranking classifier? Can you modify it dynamically on the fly? The answer is all these things you see here are my features that I'm defining. I put them in this file. I then run this, train and upload model. And I can show you what that looks like. Of course.
Are those features weighted or anything?
Yeah, so give me just 1 second. Let's see. Train upload model. One second. That's the problem. Easy to fix. Started off different port. Boom. I just built and uploaded my model. So now it is dynamically reapplied. So Solr has this idea of a feature store where you can basically take these models and push them, and then it can leverage them once you push them there. And so anytime you want to rebuild the model, you just have to retrain it, and then once it's retrained, you push it up. And the model that was actually built here, there's a very small amount of data, and there's like, a couple of, there's maybe like 6 judgments or something in the file, so it takes no time to run, as you saw. If you're doing something more sophisticated, it'll take longer to train it. But the output, example model, nope. Example trained model. So, as an example, you can kind of see some rank. So this is a linear regression test. So it's like very, very basic model. But you could also do SVMs or whatever you want here. But it basically takes the model, uploads it to the feature store, and then at query time, now that my model is there, I can rerun this, and lo and behold, it re-ranked. Now, I didn't do any special preparation for this, so the features actually kind of are awful here. So the fact that they're coming back in a different order shows you that it's working, but doesn't show you anything about relevancy. But if I go to my original query, you see, this result, then this result, then this result, and in my now I've I think I've ranked iPod. So let's see, IW2 F8V MA1, IW2. Oh, interesting. Change. Probably. Do a different search. Anyway, I'll do it at the end and we'll see an example. But it is working because the model is running. Maybe the model just isn't doing much to use these documents, or maybe I'm searching on the wrong query. But anyway, that's effectively all you have to do to build the one-to rank model. So you can, give you an example. Let's say I was searching on documents and I said, hey, I really think that documents would rank higher if I had a feature called is an executive. But I don't have a field in my documents called executive, is executive. So instead, I'm going to model a query that says, if the query matches C*O, chief star officer, or any kind of permutation of that, and that becomes my feature. Now the model can learn that feature from within my documents, from my vector space, and model it and rank based upon it. Obviously, in the long run, if that thing ends up working well, you'll probably want to add that as a field to your document to make it more efficient. But you don't have to. You can actually make this thing work. And then this is one of the ideal ways to be able to have your search engine learn based upon all these features what ranks, what should rank in what order, and then some pretty cool cutting edge stuff. So, any questions on that before I jump back into the slides?
How does the training data look like? Training data?
The training data. I'll show you what the training data looks like for this. It's pretty slim pickings. Let's see. There you go. So for the query hard drive, this document gets a relevancy score of this.
Program is 0.6 grams.
Sorry?
Is it a tool that allows to collect information from users? Leaks?
Yeah. So the question is, how do you get these
How do
judgments?
you get the
Yeah.
value? Yeah.
Great question. Let me go back to the slides. I have something on that. Oh, look at that. Obtaining relevancy measurements. So the typical way that people would do this is by having a human do it. You have a data analyst, they come in, they run a query, they see a list of documents, and they rank them based upon the relevancy, and then you generate all of this training data, and then you use it to train your model. Benefits of that are obviously accuracy. The downside is it's really expensive to pay a lot of people to do this. You're not going to be able to get down the long tail. You're going to only be stuck with a few queries. If your underlying documents change frequently, that's going to be a pain because you're going to have to, for something like an e-commerce site where you've got products that stick around, it might work okay, but over time they're going to be replaced. For something like a job search website where jobs are turning over constantly, it's basically worthless to do that on specific jobs. So it's just not scalable from a manpower or cost standpoint. The other way to do it is to crowdsource. So it's less cost. If you look at things like the signals that we talked about earlier where people are clicking on things, you can leverage those clicks as effectively votes in terms of what's relevant for a query. But there's also some known downsides to doing that. Search results are biased, meaning if someone runs a search, the odds of them clicking on the first result are higher than the odds of them clicking on the second or the third or the fourth, independent of any relevancy judgments. So you have to do some things to compensate for that bias. I've done a little bit of work on this before. This is one example of a way you can do that, where you don't just look at the things people click on, but you also look at the things people skip over. So it's called creating like a click skip graph. So if someone clicked on result number, so if someone skipped result number 1, clicked on number 2, clicked on number 3, and didn't go beyond that, then you can effectively say, well, they had a positive vote for document number 2, a positive vote for document number 3, and a negative vote for 1. They thought 1 was not relevant. And so you can use something like this to not just do positive votes for things people click on, but also indicate when people skip over something to kind of balance it out. You can also look at the specific position in which people clicked on things and sort of average over positions. There's a couple of research papers out there on specific ways to combat the bias.
But is there a tool that allows this to happen?
Is there, you mean a tool that can automatically take your signals and generate relevancy judgments for you?
Up to some degree, yeah.
Well, Fusion will allow you to collect the signals and run an aggregation to generate a file. I don't think we have anything out of the box that does this, seeing as how learning to rank just got integrated in Solr, but it would probably take you less than an hour, maybe a couple of hours to generate something to do that. If you start doing a lot of this bias correction stuff, it's a bit longer, but it's all doable. The hard part is getting those signals to begin with and collecting them and having them in a place where you can leverage them. So that's, it's going to be 90% of the work. Yeah. So the question is there a specific relevancy range, 50 or 60% that you can look at in an application? Yeah, so it depends on how you're measuring relevancy. I had a quick slide earlier about Ndcg Scores, normalized discounted cumulative gain. It's basically it's a metric which, so discounted cumulative gain is a metric which counts relevancy and penalizes you for being the more wrong you are. So like if you're wrong about the first result, it's a lot worse than being wrong about the 10th result. And like it's sort of the magnitude of how wrong you are, given that you expect things to show up at the top of the results. So you can calculate a discounted cumulative gain score on a per query basis. The problem is that it's really hard to think of that in absolute terms. For example, if I will use the job search example again because I've got domain expertise there. If you run a search on a job search website, which like dice.com, it's about tech jobs. So if I run a search for Oracle or SQL or Hadoop, then I'm going to probably find some pretty good results. If I run a search for piano teacher, I'm probably going to get approximately 0 results, maybe 1 or 2, and I'm probably going to get some teaching results, but they're not going to be about pianos. Or it might be about, teaching for a software engineer who's building some like music software or something. Like it's not a piano teacher. So the question is, what was the relevancy score for the query for Hadoop versus the relevancy score for the query for piano teacher? Was it 0.9 for Hadoop and 0.1 or 0.01 for the piano teacher? The reality is every search is going to give you the best results it can find, but when there's a specific answer that's right, that relevancy judgment is going to be higher, and when there's not really an answer, is it better to return nothing, or is it better to return the best thing you have? And those are somewhat domain-specific questions you would have to answer, and it's just really hard to say, given a scarcity of content, how do you determine an absolute relevancy score for any particular query? I would argue almost every query is going to have kind of its own range of relevancy it's going to have to deal with. So because of that, we would typically use something called normalized discounted cumulative gain, which normalizes the DCG score from 0 to 1 for each query, and so or across the queries. So in doing that, let's go to the next slide. This is an example of how you might apply this for some sort of automated relevancy benchmarking. So if you take all the queries that people have run and you calculate the DCG scores for those, and you sort of average them up over all the queries you have, you can effectively take an algorithm and measure you can take an algorithm and compare it to how another algorithm would perform in terms of the Ndcg scores that it outputs. So if you for example, wanted to go in and manually twiddle the boosts on your queries or manually twiddle the features you have, and then run this thing, you could generate a baseline from your historical query logs by looking at these kind of click skip graphs and figuring out what people thought were the most relevant results based upon their clicks, and then you can use that to backtest a new algorithm to see how it might perform. That's one way of going about this. The other way is just to use something like learning to rank, and you give it the relevancy judgments, and then it just trains the model for you, and you don't have to think about manually twiddling algorithms up and down. It just you give it the features, and it more or less does the right thing for you. Is that sufficient answer to your question? Okay. But yeah, I mean, to the point of how do you get these relevancy judgments? The way you're going to get the most accurate ones is having a human do it, but that's not scalable. So mining your logs to be able to do some of it is, an area of considerable research, and there's a few techniques out there. Next thing I want to do, while we're talking about signals and relevancy and all this kind of stuff, is jump back to that e-commerce demo I had a minute ago. Let me stop Solr. Can't find it. Back up. So I talked to you about recommendations earlier. You saw that Toshiba example. I could show you other products as well, but that was using collaborative filtering that was effectively built in Spark and then pulled back into Solr. The other interesting thing you can do is just leverage the signals directly. So you take the signals and what people have clicked on, you aggregate them to create a sort of boost for each document for a query, and then when you run your query, in Lucidworks Fusion, we have this recommendation stage which can leverage signals to boost documents up and down. So I'm going to show you an example of sort of out of the box with Solr, what search results look like when you're leveraging TF-IDF. And then if you did some domain-specific boosting, for example, I'm going to boost documents higher if the, if the sales have tended to be high. That means it's a popular product. What does that do to my results? And then what happens if I just leverage these signals to boost documents instead? You'll be able to see the impact of each of those techniques and what they've done to your relevancy. So let me... Actually, I probably already have those open.
So in these scenarios, the documents are really small, right? They're basically like impressions or something like that basically have like iPhone 7 commercial or something like that. Are they like larger documents that have?
Why do you ask?
I mean, for example, in this particular scenario, the document has to be fairly small, right? I mean, Toshiba satellite laptop, whatnot has to be like a relatively small document, right?
So the question is the document really small? It doesn't have to be. Why do you ask? It can be any. The document can be any size.
I'm relating like an impression or something like that.
Okay, so there's two collections. Let me see if Fusion is running. Still starting up. There's two collections in here. There's the main collection, my e-commerce collection, which has all my product catalog. Right. And then I've got a separate collection, which is my e-commerce signals. So whenever someone clicks on that original document, I log a signal that says, all right, this user clicked on this item ID and it was a type of click, and this is when it happened, etc. And I record all of those into a separate collection. Okay. Those are really tiny documents for the actions, right. But an original document itself could be any size. The size doesn't matter. Why do you ask?
No, okay, so I get the click portion, right, where you have a document ID or something like that. That's what you're tracking, right? But then that is mapped to a specific document, like a Toshiba average customer rating, and it has a lot of metadata associated with that, right? Mm-hmm. So in the end, you're trying to basically put together like what impression am I supposed to show on the website or something like that, right? So you're trying to like map the sequence of events to what document you want to show at the on the web page, right?
Mm-hmm. But the document size doesn't matter.
Yeah, size doesn't matter, but they're essentially like typically they're just like they're just attributes of that particular product. So that is the reason why it is small. Is what I'm trying to ask.
Let me ask you that. I'm not necessarily following the question, but I'm sure there's something there. I just need to understand better. All right.
I kind of have a question. Because if I have really small documents, and then the query is also really small, it will favor that small document more than the large documents that have the same terms.
Is the question why? Is the question why, or will this overcome it? Yeah, so he's saying, in Solr, I assume, when he runs a search, that smaller documents tend to rank higher for keywords than larger documents. Yeah. If you think back to that, the TF-IDF kind of stuff, there's also, what's it, the chord factory norms? Anyway, there's compensation in there for the size of the document as well. And so, a smaller document's going to, in general, rank higher because there's less words to distribute that over, because there's some normalization factors in there, which is just, there's a couple of different so the thing I showed you earlier with that TF-IDF stuff, that's the classic Lucene similarity algorithm. There's also one called BM25, which is now the default as of Lucene and Solr 6. There's also other similarities you can use. There's one called sweet spot similarity, which tries to figure out documents, like if it's really small, it doesn't give it extra boost, and if it's really large, it doesn't penalize it, but it looks at this area in between and you rank in the sweet spot there. You can also turn that stuff off if you want to, or you can, on your query specify a function that defines your own relevancy algorithm, or you can use something like signals or boosts or recommendations to compensate for it based upon actual user interactions and behavior, as opposed to just text and keyword matching.
So I did not get a chance to look into the contents of your book, but so do you cover any details of implementational or architectural details of how search engines are built? Do you go to that level?
Yeah, so the question is about Solr in action. In there, do we go over architecture and of search engines, how that works? Absolutely. So the book starts from introduction at the very beginning. What is a search engine? And by chapter 3 is really sort of your search theory chapter, and it talks about the inverted index, how it's built, how search engines scale, and how all these things work. So yeah, absolutely. If you want a good theoretical understanding of how all this stuff works, we try to do a pretty good job in Solr in action of giving you that knowledge as you kind of work your way through the book. Yeah.
So what hardware do you recommend for a enterprise level search engine to be in production? Like
what
hardware configuration?
What hardware? Ask me that at the break. Ask me about hardware at the break. My demo's not starting up. I'm gonna come back to that then. It's a bummer. All right. Well, I will let the cat out of the bag then. I'll show you guys in just a little bit. Hopefully, I can get the demo running again. What signals do, because it really makes your search results look much better. But as an example, this is one of our customers, Red Hat. So they leverage our signals capability. So you see this baseline. Up until about here was their sort of standard, Solr relevancy. Once they implemented Fusion and turned on signals, then you can see what that did to their relevancy going up. In this case, the relevancy was based on click-through rates, which was the most sane measure of relevancy for them. So, in general, people click. This was like for a knowledge-based kind of thing. People who click on things that are relevant to what they're looking for. People who click on things are probably indicating that those are relevant for what they're looking for. So, their click-through rates increased 200%, and they have a 91% lower total cost of ownership of all this stuff. Fewer support tickets, they're able to find the things they're looking for faster. This is just by leveraging this reflected intelligence that you get by using the signals and understanding what's relevant and what's not based upon user feedback. And I hope that I can get that demo.
What were they using before?
Just plain kind of out of the box Solr. I say that. Plain out of the box search engine. I think it was Solr, but yeah, I mean, so part of this discussion, like if you take Solr, Elasticsearch, any of these search engines out of the box, you can get up and running really quickly, and you have some search results. The problem is it's not until you get to production that most people realize, hey, this is really nifty, but these search results aren't actually that good. Like I see a bunch of results, but the ones I want aren't at the top. How do I get them there? And then they embark on this very long, very expensive journey to try to get them to get better results and have things like recommendations and signals and those kinds of things integrated. So I'm trying to give you guys some of the techniques that you can use to build something better, and obviously we've kind of codified those in Fusion. So I'm going to keep going. Next topic is semantic search. So I had a question over the break specifically about RDF triple stores and how you store those and how you use those. So someone said that they basically have RDF. An RDF triple is basically like if you think of an ontology, it can relate certain items together. You would typically, if you had an ontology, you would typically represent it potentially this way. I'm not going to actually dive into this project, but there's a project called the Solr RDF project, which allows you to effectively, let me just Google it. It allows you to take RDFs and index them in Solr and then search them in Solr. and not just search them, but are you guys using Sparkle as your query language?
Yeah.
So it's fully Sparkle 1.0 compliant, which is kind of the benefit there, or maybe 1.1. Hold on. Solr RDF. Sparkle 1.1 compliant. So you basically you index your RDF triples, and you hit the endpoint, and you can basically pass. Notice this is an actual Sparkle query. You pass in, and it can query Solr and use it as your RDF triple store, which has you get things like Solr scalability, horizontal scalability. There's a lot of benefits you get from that kind of thing. But it also allows you to stay in Solr where you're doing a lot of your other query and relevancy stuff, and leverage Sparkle there inside of Solr.
But it's either or. You either do Sparkle or you do standard query.
No. So this let's see Sparkle. So this Sparkle thing right here is a separate request handler in Solr. So you can index your data in a normal Solr collection and query it however you want to, and even have separate collections that have the rest of your data. You would index your RDF triples into a collection like this, and if you want to do a Sparkle query, you query the Sparkle request handler, and you do the Sparkle query. If you want to do just a normal Solr query, you could do that too on a regular request handler.
Come together, kind of like rank look for these two concepts, and the rank is higher. There is a relation of some sort between them.
That is a good question. So you could definitely do it in Fusion by having a query pipeline that hit this, got your results, and then modified your query. Whether you can do it directly in Solr or not, I'm not sure. If they have a query parser, then you could. I want to say they only have a request handler, though. Let me see.
You said this works if you take your RDF data and put it in Solr itself. How can you put some of the complex descriptions into Solr? Like if you have a binary relation, the left-hand right-hand side thing which you're doing, how you go to maybe create 3 fields or something?
Oh, so your question is about tagging, I think. You've got a document that passes into Solr. How do you?
Do we have the structured information? I don't know how to represent it in Solr without just turning it to a string.
Yeah. Ask me about that one at the break too. That's going to be a complex, long answer. Anyway, I don't want to actually spend much time on this one, but I did want to point you in the direction of the Solr RDF project. It sounds like you guys already have RDF triples, and you need a triple store, and you use Solr for lots of things, so it might be possible. Maybe it's not feature complete for what you need, but it's at least Sparkle 1.1 compliant, or so it says.
What about SQL then?
SQL against Solr?
Yeah, like you can do SQL in Solr?
If you stay till the very end, I've got a whole section on that. Yep. Yeah. So I'm gonna keep moving along. So that's how if you already have RDF triples, that's how you can store them in Solr. The next thing I'm going to get into though is dealing with entities and taxonomies and those kinds of things. So ultimately, to really build a sophisticated search app, you need to have a concept of what are the entities within your domain. There's any number of ways to generate that. One is you can have a team of data analysts who just by hand type a bunch of entities and build an ontology or taxonomy. That's very expensive. You can also do topic modeling, clustering documents to try to find interesting relationships within your content. You can do statistical analysis of interesting phrases using something like Word2Vec or Glove. Dice.com also released a conceptual search plugin for Solr that effectively uses Word2Vec to find interesting terms or phrases, as well as a vector of related terms that you can use to then do concept expansion for semantic search. It's worth checking out. You can buy a dictionary, though that doesn't really work for domain-specific problems. Or you can generate a model of domain-specific phrases by mining your query logs. So one recurring theme we keep talking about tonight is, hey, when somebody runs queries, those logs have lots of useful information. So one of the other things you can do is take all the queries people have run, aggregate those up, and the things that people search for the most commonly, those are probably good candidate suggestions for things that are important within your domain. If you're a product search site, those are probably product names or categories. If you're a restaurant, they're probably restaurant names or types of food, etc. So you can basically just mine those and use them. So I've got a couple of research papers I'll link to from the presentation where I've done this before. You can read those if that's your thing. We also, in Fusion, can do this as well to find queries and related queries by mining query logs pretty easily. I mentioned Word2Vec and Glove. Do you guys know what those are? I think almost everybody knows about Word2Vec these days. Okay, I'm going to skip over it. You can ask me later if you're interested. I talked about the conceptual search plugin for Dice as well. One of the other interesting things that you're going to want to do is not just know about your entities, but be able to extract entities out of documents. So, my favorite project for this is a project called the Solr text tagger. It basically allows you to take any blob of text, a very, very large chunk of text, pass it to Solr, and have Solr in milliseconds extract out all of the entities found within that text that are within a taxonomy that you have. So if you've built out a taxonomy of 10 million terms, and then I take a really long document, pass it to Solr, Solr will return to me the entities it extracted as well as the very specific position in those documents that those entities were extracted. And I have an example of this just to make it clear what I'm talking about. Let's see if I can. Okay, so here's an example. This is so I've indexed a taxonomy of data, and I just grabbed a job posting from Lucidworks website for I think it was what is this? A UI developer, a senior UI developer. So this is a lot of text. The question is, what do I do with this text? If I've got a taxonomy of things that I've extracted, can I extract all those out, and how quickly can I do it? So I'm going to take that text. I'm going to, of course, I stopped it. See if I can restart it. Okay, try this again. So I've got my Solr text tagger. I pass this content in, and then what it's done, if I bring this a little higher, in 120 milliseconds, it took that entire document and looked at all of the millions of, I don't know how many I have, tons of things I have in my taxonomy, and found, for example, the word company it found, starting at position 0, which is right here, and ending at position 7 is effectively highlighting it. It found the word company. And then the next thing it found was the word information, which is this next word, starting at position 8 and ending at position 19. So I'm effectively tagging exactly where in the document I found these things. And then if I scroll to the bottom, you can see the list of things that were actually extracted. There we go. Yeah. Apache Lucene, leverage, preprocessor, semantic HTML, text processing, web standards. Those are the things that are extracted out of this document. They're not. It's a naive entity extractor, which means these aren't in any particular order. But one of the technologies I'll show you in a minute, the semantic knowledge graph, allows you to actually take these and then rank them based upon how relevant they are for that document. So once you've got your entities, you then want some sort of entity extractor. We also have an entity extractor capability built into Fusion that you can leverage as well. And then semantic query parsing is the next thing you would want to do, which is, this isn't part of Solr yet, but there's a patch that was submitted. This basically allows you to take a query that's text, and instead of breaking the text apart, for example, if I pass in a query for senior software engineer Hadoop Solr, then those aren't just a bunch of individual words. Senior software engineer is a phrase, Hadoop is a phrase, and Solr is a phrase. And I want to be able to figure out what terms and phrases exist, how those terms and phrases should be modeled so that I can send the query to the search engine appropriately. I have a demo of this, but I'm going to skip over it just for the sake of time. I'd be happy to show you afterwards. But more or less, this works by taking like senior Java developer Hadoop, looking at all the possible parsings, and then leveraging the inverted index to figure out the statistics of how often these things appear as phrases. And so it can basically use, think of it like using Bayes' theory to figure out the probability of, the phrase being senior Java versus senior Java developer. And you figure that out with the query, and you probabilistically parse the query out based upon what it most likely is representing. It's not 100% accurate, but you can get the accuracy pretty high with some tuning. Once you've done that, you effectively have a bunch of terms and phrases that, let's skip a bit of the demo, a bunch of terms and phrases that you think you've identified from the underlying corpus. If you have a taxonomy, you can also leverage the Solr text tagger to be able to also extract out things that are explicitly in your taxonomy. And then you can look at things that were extracted from your taxonomy, as well as things that weren't in your taxonomy, but which probably represent phrases based upon the data in your inverted index. And you can sort of use one or both of those to figure out the right parsing of your query.
But did you already tell it, like that Hadoop developer is a phrase?
No, so that's the magic of this. If I have a taxonomy, I can use the Solr text tagger to extract something. But there's a lot of things people will search for that aren't going to be in my taxonomy. So the probabilistic query parser leverages the statistics in the inverted index, meaning like how many documents does the word senior appear in? How many documents does the word software? How many documents does the word developer? And then what about senior software developer? And it can look at the occurrences of them as phrases versus individual terms and use Bayes' theorem or some other statistical measure to figure out what the most likely parsing of that is. The inverted index is this, it's one of my favorite data structures in computer science because you take all of your documents, you index them in, you can do these keyword searches, but not only that, you can really learn statistical relationships between terms and phrases. And I'm going to show you, I think the next thing coming up is the Semantic Knowledge Graph, which is a project that is open source that I've worked on, which is really a really cool way of leveraging those statistics as well. So once you've parsed out the query and you've got these terms and phrases, the question is then what do you do? You can search for them as text, but what if somebody typed in the wrong word? Or what if there's a document that really represents what they're searching for, but it doesn't have the exact words they search for? So what you need to do then is some query augmentation or query expansion. So this project, the Semantic Knowledge Graph, it's contributed as Apache Solar, but it's not part of Solr yet. What it allows you to do is effectively leverage those underlying statistics in the corpus for things like character sequences, specific terms, sequences of terms, which are phrases, and understand those interrelationships and score and rank them. So as an example, here's a couple of this is from a research paper that we published earlier this year. But I've got 3 different documents here. One is, anyway, you can see the 3 documents. I take those, I put them in an inverted index, which you see represented over here on the right. We already talked about the inverted index earlier. I also put them in a forward index, which is an index that has the document mapped to the term. So I've got terms mapped to documents and documents mapped to terms. What that allows me to do is actually traverse either way. So if you think of a facet in the search engine, the way it works is you run a search, you get a list of documents, and from those documents, you then traverse to the list of terms found within them, and you aggregate those and get the counts. It's the sort of the opposite of the way that a search works, where you create the keyword and then you try to find the documents that it maps to. But what you can end up doing, because you can go both directions, is you can actually do things like multi-level faceting in analytics, as well as collecting term statistics along the way. So this is a graph, semantic knowledge graph. High level, how this works, and some of this is going to be a little academic, but I won't get too deep into it. This is 3 representations of what this graph looks like. Excuse me, what it looks like. Over here I've got my data structure view, where I've got something like the skill of Java mapped to a bunch of documents, and similarly I have a bunch of other skills that are mapped to the same documents. And I can leverage these corpus statistics to figure out which terms are the most related to that original term. The naive thing to do would be just to count them all up, given the skill of Java, which other skills are overlapping the most number of documents. But there's a more interesting way to score this stuff using effectively like a z-score or a distribution calculation, which I'll show you in a second. So that's the data structure view. The set theory view, this is how the sort of bit sets intersect and overlap of the documents when I run my query, as if it were a Boolean query. And then finally there's this graph view, which shows me that I have a node for the skill of Java that has a relationship of has related skill to the node of Scala, and another relationship of has related skill to the node of Hibernate. I've got this skill called oncology, which is not connected in the graph. And then Java obviously is related to itself. It better be. I'm going to skip over the model and the scoring. I'll just give you the high level intuition here. So what I can do with this graph is I can say, all right, starting with the skill of Java, I want to find all the most related other skills associated with it, traverse to those, and from each of those, I now want to find the most related job titles associated with those. And you sort of traverse this graph of relationships purely based on the inverted index. Just to reinforce the fact here, I have not manually built a graph. I have not modeled these relationships in any way. All I've done is taken documents that have a skill field and a job title field on them. And I have indexed them into an inverted index. And all of this graph is being materialized dynamically so that I can mine these relationships. And this is the graph view of what you see over here. I have the skill of Java is related to the skill Hibernate, which is related to the job title of Java developer. The interesting thing comes not when I look at just these relationships, but in how you score these relationships. And for scoring, here's the intuition. It leverages, think of it as a z-score, and this is the math calculation here. This is all open source, by the way, so you can download it and play with it. I'm effectively doing a foreground background analysis. So think of it this way. In this case, I've got a query of Hadoop, and I've got a bunch of other keywords that I'm traversing to. And what I want to know is how related are each of these keywords to the keyword of Hadoop? From an intuition standpoint, think of this as how often does the keyword Hive appear in documents related to Hadoop relative to how often the word Hive appears in documents not related to Hadoop.
How is that different from word to length?
It's very similar. You get similar kinds of output here. There's some really interesting, hopefully I'll have time to get into it. There's some really interesting things this can give you that word to vet can't. You also don't get the sort of some of the vector calculation stuff here. So they're different in implementation, but similar in concept. And so similarly, how often does the word CPR occur in documents related to Hadoop relative to in documents not related to Hadoop? So that's the intuition behind what we're asking. And the answer is Hive is very statistically correlated with Hadoop relative to other documents. CPR is very statistically, or is negatively correlated. So like here you get something closer to -1, and for Hive you get something very close to +1, saying the strength of that relationship. So I've now taken the inverted index in the search engine from something that takes a query and scores its relationship to documents to something that takes a query or term and scores its relationship to other terms or queries. And when I run this sort of analysis, you saw that you could do a multi-level traversal. When I run this sort of analysis, I get something interesting like this, where I need to talk about materialized nodes. Come back to that in a second. Where I start with something like software engineer, I traverse to a bunch of related skills, and from each of those I traverse to a bunch of related titles. This sort of like multi-level graph relationship traversal between terms. And not only that, but each of these terms doesn't really have to be a term. If you remember going back a few slides, the conceptual view of this, this is the graph view, but really it's underlying it's just a set of documents that are in the relationship between, which means that a node isn't just a term. A node is really the representation of a term as a set of documents that's contained within. Which means that I could insert an arbitrary node here on the fly called Java Developer and C# and CEO. And that could be a node in my graph that I've just materialized on the fly that I could connect and relate to anything else in the graph. So what's that?
Are these facets in a way?
They're fast. Yeah. So think of this conceptually as I'm doing faceting. I do one level of faceting, and then I do a pivot facet or a nested facet or aggregation to another level. And except for instead of scoring the relationship, instead of saying I'm going to get my top 10 results here and then go down a level and get the top 10 here, I'm saying I'm going to get my top 10 here based upon how related they are to my query. And then for each of those, I'm going to get the 10 that are the most related to them along some other dimension or axis. But yeah, it's basically faceting with some scoring as part of the traversal. Yep. Turbocharged faceting. There you go. But yeah, it's the same fundamental concepts you use for faceting, and yeah, absolutely.
When you add another node to Java Developer, right? Will there be any impact on the score that's being calculated?
Nothing higher up. So there is an interesting capability here. When I score a node, I can score it two ways. I can say, give me the score of Java Developer related to C#, which is how you would tend to think of a graph, where Java Developer here is disconnected from that original node. I'm scoring C#'s relationship to software engineer and Java Developer's relationship to C#. That's how pretty much all graphs work. One interesting thing you can do with this is you can actually have dependent relationship scoring, which means I can say, find me the node C# related to software engineer and get me its relationship. And then when I score the relationship to Java Developer, don't just score C#, score C# within the context of software engineer. So as I traverse through this graph, I can actually effectively, I'm doing a relationship of Java Developer to C# and software engineer. And I can do that as part of the graph traversal, as part of the scoring mechanism. I could work in either mode.
I mean, is it something like, given that this guy's good at .NET, how good of a Java developer he is, sort of thing? Or no?
Yes. I mean, it's not a guy, but yeah, it's within documents. But it's you can say, given that somebody is a software engineer with C# skills, how relevant is that to Java developer? That's the question. Yeah, it's the same thing. And so it allows you to do some really interesting things. So going back to why I brought this whole thing up, we talked about concept expansion. Imagine I run a query, I do that probabilistic parsing to parse the pieces out, then I take each of those pieces and pass them to the semantic knowledge graph and say, hey, I search for Hadoop. What's like Hadoop? What keywords are most relevant to Hadoop? Oh, Hive, Pig, machine learning, HBase, big data. And then I can take those and expand my query to do a concept expansion, to search for other things and do semantic search that way. You can find all sorts of documents that don't even have the word Hadoop, but which have people who are relevant. One of the other interesting things you can do is document summarization. So I showed you that Solr text tagger a minute ago, how it was a naive entity extractor, where if I've got something in my taxonomy, it finds it, but it might find thousands of things. I can't turn around, say I want to do a content-based recommendation, where I take a document, and I want to then turn around and search for other documents like it. That's a really dense vector, and it's going to be really slow to do. What if I want a nice, small vector that's only like the most important features? Well, take the Solr text tagger, extract out the 1,000 entities from your taxonomy, and then take those 1,000 entities, pass them to the semantic knowledge graph, and say, hey, here's a document that's about, what's my example? Here's a document that's about a big data engineer, and here's a bunch of entities I've extracted out. Please score all of these for me relative to how related they are to big data engineer. So I can take this document, extract all these things out, pass it to the semantic knowledge graph, and what I get back is a ranked list of keywords. In this case, data engineer, Hive, Pig, Hadoop, MapReduce, NoSQL, HBase, Impala, Python, Cassandra, Scala, machine learning, Tableau, Mahout, analytics, Java. That's a pretty nice, clean list, right? You can see it in sorted order of relevance for the document, the terms found within this document, how related are they to the topic of the document, which in this case is the title. That is my vector that I can then turn around and run as a keyword search against this search engine / recommendation engine spectrum, right? I run that as a keyword search, I get really, really accurate content-based recommendations based on nothing more than the underlying statistics within the inverted index. There's no reflected intelligence, no query logs, nothing of that. This is all just purely content based.
So in the search query, you only did the big data engineer, or did you send the whole?
Big data engineer.
That's it.
Yeah. So my query to the semantic knowledge. Yeah. I'm going to skip the demo because I've got an example here that will show you. So this is what, on the open source version, if you go to the GitHub account, this is what a query to this thing looks like. So in this case, I'm querying for the keyword of data scientist, and I'm saying, find me the top 1 job title related to the query of data scientist, and then for that job title, find me the top 5 skills most related to that job title. And also, in addition to those 5 skills, look for Java, the programming language, and rank that too. That's what the syntax tells you. And the result is, okay, fine, the top job title associated with your query of data scientist is data scientist. Okay, yeah, good. If that wasn't the answer, I would be concerned. That's the most relevant job title to the query of data scientist. For that job title, here's the top skills that are found within your corpus of data. Machine learning, predictive modeling, artificial neural networks, Apache Hadoop, and Java programming language is here only because I requested it. If I wouldn't have done that, it would have been something else. Notice the scores. Machine learning relatedness, 0.97. Predictive modeling, 0.94. Artificial neural network, 0.94. Hadoop, 0.94. Java, 0.76. There's probably a whole spectrum of things in between there that are more relevant, but I only asked for 5 back.
So that can be used to say how important Java is to a data scientist. And
Yeah.
basically say it's not very important.
Absolutely. Yeah. Again, as represented by your content. If your content, like if this is, for example, job postings and it's representative of the market, then yes. If I'm on dice.com and they only have tech jobs and I'm looking for a teacher, I'm going to get wacko results. It's not, your corpus has to be representative of the domain. And there also have to be overlaps between things. Like if I index Wikipedia into this thing, it's actually not going to work that well because Wikipedia articles, there tends to be 1 article about every topic. Sometimes there will be a little bit of overlap, but it's rare. So if I index Wikipedia and try to traverse relationships, there are no relationships. Everything's more or less independent. Therefore, it doesn't work well. So it would work well for something like this. If you think of like a Stack Exchange or Stack Overflow where people are asking similar questions about related topics, it would work well for something like that. But you have to make sure that there's sufficient overlap of the way that language is used in your corpus for the store, the semantic knowledge graph. It learns the semantics of the underlying data within your corpus. And then obviously you turn around and do something like I was showing earlier where I'm in Fusion now, I created a semantic search query pipeline, I got my query fields, my facets, and then I create a semantic concept expansion stage. What does that do? Well, it parses out my query, tries to figure out phrases, passes those to the semantic knowledge graph to find related terms and phrases, expands the query to Solr, runs it, and then I get my list of results. So what you can see here, I ran a search for detergent for clothes, trying to be clever. This over here is my default list of search results. This is what I would get with Solr out of the box. Over here, with this concept expansion, I notice here I got laundry detergent. Okay, that looks good. Dishwashing detergent. That's not right. And dishwashing detergent again. So that's what my results look like here. Versus with the concept expansion, I have laundry detergent, laundry detergent, laundry detergent. And it learned probably from the word clothes what was related here. The word detergent was related to clothes, or maybe it probably boosted clothes or so. I don't actually know what it did. I'd have to look at the code, but you get the idea. You can use this for building out semantic search capability. And that is, let me see if that demo ever loaded. Huh, that's interesting. Oh, I know why. Yeah, another port. couple other topics to go over. Any other questions on this semantic stuff? I'd be happy to talk with you guys after. Yep.
Performance-wise, is this better or faster than the dice.com option with Word2Vec and
Okay, interesting question. The question was performance-wise, is using the semantic knowledge graph faster or slower than the DICE conceptual search stuff using Word2Vec, or basically anytime you would generate terms with related vectors. It's slower, but you're still talking, probably milliseconds. If it's definitely sub-second. The interesting thing about the semantic knowledge graph relative to something like Word2Vec. Do a thought experiment. When I say the word apple, what does that mean to you? What do you think of?
iPad.
You think of an iPad. When I say the word apple, what do you think of? Fruits. A fruit, okay. When I say the word apple, what do you think of? MacBook. If I'm an employee of Microsoft and I say the word Apple versus an employee of Apple and I say the word of Apple, it means something different. Like, it's the same company. Like, you think of it as like, all right, there's this company called Apple, and if I'm building an ontology or taxonomy, then people tend to think, and whenever you build models, people tend to think, okay, Apple is a company and Apple is a fruit, and that's all Apple is, and it falls into one of those two buckets. But in reality, I would argue, and this is more of a philosophical argument, that the meaning of a word is different in every single context in which it appears. Even, when I say Meetup, and I'm standing right here, it means something different than when I was in my hotel room trying to get these demos to work before coming here tonight. Meetup meant something very different then versus me standing here speaking now. And I would argue every single context in which you see a word determines what its actual meaning is. So the semantic knowledge graph, what it allows you to do is say this word within the context of these other words. But the context is all the documents they're found within. So literally, if a word is found within 1 million documents, and I cut that into 100,000 or a different 100,000, there's going to be a heavy overlap of meaning between those documents. But based upon how I carve it up and what my exact context is, there's going to be a nuanced different meaning. Which means, in one context, like take the word, take the word Java. If I am a user and I run a search for Java, I run a search for C++, and then backend, and then C, and then embedded, and then Java, versus someone else who runs a search for jQuery, and then HTML, and then CSS, and then Java. Java actually means something different to both of those people. It's still a programming language, but they're coming at it from a different perspective, and they're thinking about it in a different way. And so what I can do with the semantic knowledge graph is say, given all this other context I have about the query, let me find the meaning of Java that fits this dynamic context which I just constructed. And then once I've found that, let me relate that concept of Java to some other concept of something else that I've just constructed. It's this ability to dynamically materialize a graph where the meaning of each node in the graph is different based upon every possible context it could exist within. And by the way, you have embedded all of the linguistic data associated with those documents in that inverted index. And so you can leverage it to do very nuanced things. If I query for the word driver, one context that might mean a golf club. In one context, that might mean someone who drives a truck. In one context, that might mean a taxi driver. One context, that might mean an embedded software driver or printer driver or something. And I can understand that with the semantic knowledge graph.
And then you can basically keep selecting and going in one direction as opposed to
exactly.
That's what this gives compared to Word2Vec.
Yes, what Word2Vec gives you, typically you would model things as entities and then model a vector of relationships. And yes, you can take a couple of vectors and do vector math and multiplication or whatever, and you can find other things related to them, but you've still effectively modeled everything as specific meanings associated with those vectors, which greatly limits your space of understanding. It still works well. I'm not saying it doesn't work well. It does, and it's used for all kinds of things, but this gives you an extra level of nuance that is really useful when you're dealing with search and relevancy and understanding user intent.
This is a whole topic.
Yeah.
Everybody's interested in this. I've studied it
Awesome.
at Brainspace quite a bit.
Have I said anything that's off base?
There are a couple of things I can argue with, but
okay.
I think this is a Solr conversation, not a semantic conversation.
Sure.
So if anybody's interested, I'll talk about it.
Okay, sounds good. Anyway, semantic knowledge graph, open source, Solr plugin, download it, play with it. If you have questions, feel free to email me or what have you. Hopefully it'll be in Solr one day, but you can use it now if you want to. And I still didn't kill it. That's okay.
Some of the things we studied at Brainspace was similar to things to the semantic graph. Except we built implementation called spreading activation. What is a graph that you start off with a search node and you copy it out and you find other things that are similar based on how properties.
Yeah, very related.
Very, very similar.
Yep, very similar. You know, it all makes sense, and various incarnations of this have been built over the years. But I'm trying to bring it to the masses by open sourcing it. Okay, streaming expressions. Another interesting thing about Solr. By the way, just topic-wise, we've got streaming expressions and Solr SQL and graph are the three things remaining, and then you guys can go home. And if you don't care about any of that stuff, you can go ahead and leave. But just to give you some context. All right, Solr streaming expressions. Do you guys know what these are? Is anybody here familiar? One person, sort of. Okay, I'll explain streaming expressions to you. Streaming expressions in Solr allow you to perform relational operation on streams of data. An example of the kinds of, there's two things, there's sources and there's decorators. So imagine a field across all of your documents, and all the values in that field can be pulled out as a stream, and then you get that stream of values from a source, and then you can do processing. Think of it like MapReduce, distributed MapReduce, where I'm doing function operations on values from the inverted index. So, or doc values in this case. So, and stream sources can be a search. I run a query and I stream the values that are the result of that query. Facets, I'm doing an aggregation of values from a field. Features, which is something used as part of training a machine learning model. Gather nodes is used for graph traversals. Shortest path is graph traversals. And then train features and model are all based upon building machine learning models. And then topic allows you to subscribe, kind of a hubs up kind of thing. And then stream decorators allow you to take those values coming out of those stream sources and do interesting things like classify them, do joins, do distributed joins, merges. What else is interesting in here? Scoring. If it's a graph traversal, you can score nodes. This scoring uses TF-IDF, though it could be extended, and do other interesting kind of calculations. So this is an example up here of a streaming expression. I'm doing a hash join. I'm running a search, and then I'm hashing on this second search and joining on movie ID. And you can kind of see from the admin UI how the plan for this, how the query execution plan looks. Nuts and bolts of this in Solr relies on doc values. So I'm not going to get into what doc values are, but they're on by default on all non-text fields. And you get really good read performance if you're trying to look at lots of documents or export lots of documents. And it allows you to use your entire Solr cluster. Where you've got distributed shards and replicas, you can leverage all the workers within the cluster to do these really fast distributed computations. Here's a couple of examples of different kinds of things you can do with streaming expressions in Solr. Normally you think of a search engine as, hey, I send it a query and I get results. We talked earlier about how you can also do recommendations and all these other interesting things. This is an example of effectively doing processing, leveraging functions. So just a series of wrapped functions that do interesting things. So this first query, this first streaming expression that I can send to Solr is running a search and then using a machine learning model to classify the results of that search, and then I return classifications. The second one is a graph traversal where I'm querying my collection from documents related to John at company.com, emails that were sent to jane@company.com. My edge is the from and to address, and I want to traverse between those to find related emails. This next one is a distributed join. So I run a query and I need to do a join across 2 different collections and bring the results back. The one below it is pulling results from external database. So actually, I can actually run a query, use JDBC to pull data from an external database, join those results and do something interesting with them, and then return that from Solr. Down here is an example of training a logistic regression model. This middle one is rapidly exporting all search results. So one thing search engines historically have not been good at is getting a dump of all of the results. They're really good at returning the top results of a page, but not good at returning millions and millions of records. This is a lightning fast way to just export everything that's the result of this search query. And then this last one over here is particularly interesting, and it's hard to read from there, but you guys will see the slides after. This is a topic that I can subscribe to. I'm selecting values from that topic. I'm updating a collection with the stuff that I selected out of there. I'm running a daemon, which is a long-running process that can continue to do work on that, and then I'm doing that all in parallel. And so what that effectively gives me by combining those streaming expressions all together is parallel batch processing, where I've registered a batch process that's running in the background and in parallel doing all of this work and updating a collection, and it just keeps running until I kill it, or until it's done, if I tell it to finish when it's done. But imagine that. Just by sending a query into the search engine, you've effectively built a batch processing capability, just by chaining these functions together in the appropriate way. So this is actually one of the most actively developed areas of Solr right now. Lots of new expressions are being generated all the time, but what it really gives you, if you think of the core of Solr as running a really, really fast query and ranking results and returning them, what this gives you is the ability to do all of the things that you would want to do that you can't do with that real-time model. And these things will typically not return in 1 or 2 milliseconds or 10 milliseconds like a normal search query would that only hits the inverted index. But these will still often return in seconds, and for really complex jobs maybe longer. But you can use this to do batch processing and parallel computation, MapReduce kind of things on the data that's in Solr. Yep.
Could you explain the distributed join up there?
Sure. So I'm basically if I've got a query that goes against the search engine, I'm hitting one collection, and I'm doing a query, and I get results back from that collection. If I'm running them against another collection, I can do the same thing. But what if I want to get results that are a join between the two? There's no good way to do that with a typical search engine. So this is basically it's running a search on the people collection, and then it's also running a search on the pets collection, and it's doing a hash join, on the search collection, joining on person ID. So it's basically running the search on both collections, streaming the output, and then doing the join on the streamed output before returning the results across different nodes across the cluster.
Could you do like a join like that with the external JDBC?
Yeah, you could. Now, depending upon the speed of the JDBC connection, and it might be slow depending upon how much you're streaming, but yeah, absolutely. Some pretty cool stuff here. So I'm just scratching the surface on what you can do, but I mainly want to just kind of expose you guys to these capabilities. And nothing like this exists in any other modern search engine you're going to see, short of pulling all your data into Spark and trying to do it there, which you can do. But this stuff's kind of built natively into Solr. One of the things built on top of streaming expressions is Solr SQL capability. So the question is, hey, can you run SQL against Solr? The answer is yes, kind of. And by yes, kind of, I mean you can run SQL. Let me talk about what you can do first, and then I'll talk about some of the caveats. So yeah, pretty much everybody knows SQL in this field. If you don't, you have to learn it at some point along your career, usually very early. One of the hard things about search engines, and Solr in particular, is the learning curve of, hey, this thing has its own query language. How do I do faceting? How do I do nested faceting, pivot faceting, distributed faceting? All these capabilities that are really powerful, you have to learn. What if you could run a SQL query, get results sorted by relevancy on some random function, apply a geospatial filter? What if you could do all the things you could do in Solr as part of a SQL query and return that? You would get most of the benefits of the search engine in a language that you already know and understand, which would greatly expand the audience of people who would be interested in leveraging the search engine to do this relevancy kind of stuff. We have the title of the talk was the Apache Solar Smart Data Ecosystem. We've all talked about big data for years. Big data, where you just get a bunch of data and put it in a place, doesn't actually do you any favors. It just becomes this unwieldy thing you have to maintain. The important thing is relevancy. The important thing is, how do I get value out of that data? Where are the smarts? I would much rather have a 1 terabyte collection of data that I could deliver, that I could get really useful insights out of, than a 100 or 1,000, ginormous, many terabyte collection that I have no idea what's in there and don't know how to get access to. So, being able to use something like SQL to expand out the audience of people who can leverage search is something that's really important and that Solr is striving for. So here's an example of some queries you can run against Solr directly. So this is a typical search you would send to Solr for, I want to filter on genre and rating, and I want to facet on the titles. So this is basically saying I want to aggregate values on the title field. That's normal Solr syntax, and this is SQL syntax in Solr to do the same thing. There's a couple pieces that are a little wonky, but you can issue a SQL query to get more or less the same thing. And over here, same kind of thing. Here's my results, and here's the results I get back from the SQL endpoint in Solr. Similarly, I could say in SQL, give me the average rating for men and women over 30 for romance movies. Give me the top 5 rated movies with at least 100 ratings. Give me the set of unique users that have rated documentaries. There's group bys and those kinds of things. One thing you'll notice in here is there's not joins. And so the Solr implementation of SQL right now has not yet implemented joins, and there's a lot of other SQL semantics that haven't been implemented yet. They will be at some point, but it's fairly limited. It's powerful, but it's also limited right now in terms of what Solr supports. Just because this is a relatively new capability and it's still in development.
Gotta pull the SQL guys out of SQL. Not the other way around.
Well, there's utility. I mean,
Tableau.
Yeah, and that's where it gets really interesting is in things like external tools like Tableau, where you can just point Tableau at Solr or at Fusion or something like that, and actually use it and get all the search benefits. It's not just the language; it's also the ecosystem, right? So it's really powerful. Also, you can be naive and still get the answers without having to be a Solr expert, because Solr experts are expensive. Yeah.
How would you do like a full text search query? Would you still be able to get to the text field?
Yeah, so effectively every time you see an equals, it's running a search. Right. So when I say genre equals romance, it's doing a search on that field for romance.
But you could do it.
So you could, for example, put where some field equals, and you could actually use Solr. Solr's got a query parser syntax where you can basically have it invoke a different query parser. You could pass that in here, and it passes through to Solr, resolves the results and returns them up. So you can basically inject Solr specific things into here anywhere you would want to, as if it were a term you're looking for, but really it's a query that you're executing. Here's how do we use the streaming API in Fusion? Leveraging Solr. I skipped a slide. That's not important. So we have the Spark Solr project, which is open source, that if you're just wanting to, not use Fusion, but you want to leverage, Solr as an RDD for Spark, you can download the Spark RDD. You have to figure out how to integrate it yourself, but it's not, you can do it. And that allows you to use the streaming API. We also perform aggregations of signals, which we talked about earlier. For example, clicks to compute boosts and recommendations using Spark. And then we've got some custom Scala scripts to be able to do some more complex analysis. We also have a visualization framework called Banana or Silk integrated into Fusion. And also with Fusion ships with a SQL endpoint of its own, which is a more advanced version of what you have in Solr. It effectively combines Fusion and its security model with Spark SQL and uses our it uses our knowledge of Solr to be able to push down computation from Spark SQL into Solr to get lightning fast resolution of queries. Things where Spark on its own, if you're pulling from any other RDD, would actually stream all the values in and do the join in Spark. We can actually push those computations down into Solr to make them lightning fast based upon the inverted index. And get many times faster SQL queries coming back. So
it's creating an abstraction of RDD, but it's actually not an RDD, is what you're saying?
It is one, but you can basically have, when it's trying to do certain operations, you can push those down to the underlying engine to return the values out. Yeah. Question?
What's the earliest version of Solr that this would work with? The Spark Solr or Spark SQL?
Well, it depends on doc values, which originated in the 4x line. I'd have to pull up the Spark. Guys on my team would know the answer to this question, but I'd have to pull up the project and look at it. It is open source, the Spark Solar project, so you can look at it and figure out how to integrate it. Definitely the 5x line. I'm guessing it probably goes back to the 4x line, but I would highly recommend using something in the 6x line because it's newer and a lot of the efficiencies. Like basically every new version that comes out, it gets faster and faster because there's more performance improvements in Solr than it's able to leverage. So newer is always better.
Most of the Hadoop distributors are not caught up to the 6 version.
Yes, I'm aware.
Yes.
I agree. Hopefully they'll get there. Okay, so that's the Spark Solar project we talked about. And just really quickly comparing capabilities. There's a bunch of different SQL kind of engines out there in the NoSQL and big data space. Solr we just talked about has complex query constructs. Allows you to push complex query constructs into the engine. So full text, geospatial, relevancy, graph, functions, those kinds of things. The SQL features are evolving. They're not mature yet. You can use them if you know what you're doing, but you'll probably run into some issues if you try to do anything overly sophisticated. And then it scales linearly. You just keep adding nodes and replicas and boxes, and everything scales very well. You don't need, like with most SQL engines, they scale up and you have to get really beefy boxes to be able to run them. That's not the case here. And then there's a JDBC stream source that you can hit. Hive and Drill I'm not going to get into as much. Spark SQL, in contrast with Solr, uses the Spark core. It's more mature than what's in Solr right now, but it's also very memory intensive, and it scales out using the Spark cluster and it's backed by RDD. So really the underlying RDD and data source that you're using for Spark is going to dictate your performance here. Solr happens to be lightning fast because of how it's built. And so using Solr as an RDD for Spark gives you a lot of speed benefits and all these other search capabilities that you wouldn't have normally. But in Fusion, we actually combine them all together. So you get the benefits of Spark SQL plus the Solr benefits plus enterprise security, and then we also extend out this thing called an analytics catalog API, which allows you to effectively register either a Solr query, a streaming aggregation, like those complex things you saw a minute ago, or another SQL query. You can register those as a view and then query against that. So you get this sort of additional layer where you can build some really complex queries to represent data and joins and those kinds of things, and expose them out as this very simple table that a business analyst or anybody could really easily query, and that thing can be cached and so on. So it's pretty sophisticated, and I'm not going to do a demo right now just for the sake of time. I might be able to do that afterwards if people hang around, but I'll continue on to talk about Graph for those of you who want to get out of here. This is the last topic. So we talked about streaming aggregations, and we talked about how the SQL capabilities in Solr are built on those streaming aggregations. So whenever you issue a Solr query, it's actually doing a streaming aggregation under the covers to collect all the data and return it. The same is the case for a graph in Solr. So some common graph use cases include things like anomaly detection, fraud detection, recommenders, social network analysis, graph search, relationship discovery and scoring, like we saw with the semantic knowledge graph, and access control. So the ability to say, a user has access to, a user belongs in this group, and this group has access to these documents, and when that user comes to run a search, we need to filter the search based upon that relationship that's not directly in the document you're searching. And I've got some examples here. Find all draft blog posts about parallel SQL written by a developer. Find all tweets mentioning Solr by me or people I follow. Find 3-star hotels in New York City my friends stayed at in the last year. If you've got these relationships modeled as documents in your index, you can query across those relationships and ultimately get more relevant results. So Solr right now is on release. The version is 6.3. I think 6.4 is coming out in about a week or two. Just in terms of timeline, Solr 6.0 introduced this thing called the Graph Query Parser, which allows you, in a normal search query, to execute a graph query as part of your query, almost like a keyword. So am I going to match documents? And the match is based upon a graph traversal. Separately from that, there's this other graph capability called the graph streaming expressions, which allow you to take all the data that's in your index and to be able to do distributed graph operations and traversals on that. So the latter is more for kind of, let's call it discovery sort of workloads where I'm trying to mine and find relationships in my data, whereas the former is more for real-time search and returning results based upon the match on a graph. And we talked about the semantic knowledge graph earlier. That's not in Solr. There's a patch available. That's kind of a pet project of mine. Hopefully we'll get it in there at some point. So the graph query parser, which we talked about, provides query time, cyclic-aware graph traversal, and allows you to rank documents based upon relationships. It provides controls for depth filtering of results and inclusion of root and leaf nodes. And the one limitation, which stinks and is being worked on right now, is that due to the nature of this problem, it's actually somewhat hard to do this in a distributed manner. So the graph query parser only operates within a single collection today as part of its ranking capability. There is an implementation out there that is able to work distributedly, but it's not, for various reasons, it's not in Solr yet. But hopefully that'll come at some point. So, here's some example queries.
So you collect everything in one node and then?
Right, so this is useful, for example, a good use case is ACLs, access control lists, what I was just describing. I've got documents with a group stamped on them, and then I've got groups with people in them, and I want to be able to run my query as a user and then only get results back I'm allowed to see. And so what you have to do in that case is take the documents that represent the groups with users in them and put them in the same collection as separate documents alongside your actual documents. So you still get the benefits of being able to decouple. It's just that, let's say I had 10 different collections that I needed to be able to join this relationship on. I have to then take those documents I'm going to join on and actually put them in all 10 collections, which is, it's doable, but it's somewhat of a limiting factor. It's just, it makes your data modeling a little bit harder than it has to be. So hopefully we'll get that distributed at some point. So that's the graph query parser for real-time queries, doing graph traversals, and leveraging that as filters and as far as scoring. And we also have graph streaming expressions. So these implement a very powerful breadth-first traversal that is able to work across shards and collections. Here's an example of, actually what I put there. Let me skip over that. Okay, so here's an example. So find all movies that user 389 watched. So this is, I indexed a collection of movies, the Movie Lens data set, if you guys have ever played with it. And I want to find all movies that user 389 watched. I do an streaming expression called gather nodes on the Movie Lens collection. And I'm walking from user ID 389, and I'm gathering the movie IDs from that traversal. If I want to get more sophisticated, I can say all movies that viewers of the movie The Air Up There also watched. So The Air Up There is movie 161. So my expression here is gather nodes on the Movie Lens collection. Then I'm going to do another gather nodes on the Movie Lens collection to find all of the nodes that all the user IDs who watched The Air Up There, movie 161. And then from those, I'm going to walk to the movie IDs of that those users actually watched. Excuse me. We talked about collaborative filtering earlier and doing that in Spark and pulling that data back in. You can also effectively do, now this isn't performant if you're running this over and over, but if you want to run it one time, then my collaborative filtering here is get the top 5, do a graph traversal, another graph traversal. I'm not going to go into all the details of it, but effectively I can go through my content, and by combining these streaming expressions and these graph traversals, I can build a collaborative filtering algorithm just based purely on this. I could then potentially do an update and save those results off into a collection and leverage that collection to do recommendations in a more real-time fashion. Some really powerful stuff. And so, getting back to choices here. So there's a couple that I think are pertinent. Obviously, we've got Solr on the left. Elastic Graph. If any of you guys play with Elastic Graph or know what it is?
Yeah, we had a brief discussion of it the last month.
Okay.
When Elastic came into
Okay, very cool. So
it was very brief.
So Elastic Graph is, give it a high-level summary. Think of the semantic knowledge graph I showed you guys earlier, where you can take a term and you can traverse other related terms and score those relationships. Elastic Graph's capability more or less does that, but it really does it in a UI. So they've got this plugin for Kibana. You go into the plugin, you look at one level of relationship, and then if you want to expand the relationships out, it'll go and actually execute another search to paint other relationships and visually represent them. The multi-level traversal is really happening more in the user interface because it's running sequential searches to populate, whereas the semantic knowledge graph is actually traversing all the levels at once. But it's conceptually a similar thing. But it's also limited in that case to understanding these term relationships, whereas something like Solr's graph capabilities are literally having documents that model the relationships and traversing between those documents and filtering those kinds of things. So the semantic knowledge graph is a graph, but it's not what you would typically think of when you think of a graph database. Similarly, Elastic Graphs it's traversing a relationship graph, but it's not the same thing as having a graph database where you can actually traverse between document modeled relationships. It's also a commercial plugin for them. So I don't know if it's open source or not, but it's not. Okay, I know you have to have a commercial license to run it. I didn't know if the source code was out there, but it sounds like no. So anyway, it's proprietary, but so is a lot of life, including Fusion. Neo4j, a lot of people are familiar with that. It's GPLv3, which might be a problem for some folks. Spark GraphX is a pretty good graph library, depending again on the backend RDPs that you're leveraging there. Solr's graph capabilities are pretty sophisticated, and if you need to do anything that requires text search or relevancy or any of the other stuff we've talked about, I would highly recommend you check out Solr for your graph needs as well. And that is it. For anyone who's interested, I'm happy to stay and talk afterwards. I might have a couple of demos I could get running that I skipped over. I think I said at the beginning if I got 4 of 6, I'd be happy. I think that's about what I got. So I think I've got the other 2. I can get them running. Just need a few minutes. If any of this is interesting to you, I've spoken on lots of other occasions about some of these topics. Everything from analytics with Solr to collaborative filtering to this is the talk I mentioned earlier about multilingual text analytics and how you would go about searching multiple languages within the same field. Some of that's included in there. Some more reflective intelligence talks and some semantic search stuff that we did back when I was Extrovert Builder is up there too. So feel free to check those out. 2 last things. One is I've got 2 copies of the book for folks who stay after, ask some interesting questions, try to stump me. Also, if you don't get one and you want a copy, you can use this discount code 39 Grainger. You can take a picture, or I'll post the slides in a few days.
It's on Periscope too.
Yeah, it's on Periscope too. You can look at the video. And otherwise, one last thing, I did want to do a plug. So I am speaking in April at a new data science conference being held in Atlanta called the Southern Data Science Conference. We've got a really good lineup of speakers from the Bay Area, the Southeast, from all over. It's pretty cheap. I think it's like $250 or so. Don't quote me on that. But they're doing early bird signups now. So if you're interested, definitely check it out. It's I'll pull up the website real quick.
You put it up on the Meetup?
Yeah, and we'll put it up on the Meetup as well. You know, it's our first year doing it, and we're trying to make it as good as it can be.
Is it like Lucidworks specific?
It's not Lucidworks specific. I'm helping to sponsor it. I live in the Southeast, and so we're trying to get up and running. But it's April 7th, and we've got a lot of.
There's one happening next week, Scott. Do you know about the AT&T thing that's happening in Austin?
There is the NLP conference, Data Geeks.
I'm going to that.
You're going to?
Heading there? There's a day-to-day event Saturday, and there's a health version Sunday.
Yeah, Day-to-Days, right? And are they having the Graph Day also, or like they did last year?
I have not seen it, but they.
Yeah.
So it's, anyway, it's southerndataScience.com. If you're interested, you want to come to Atlanta and check it out. Otherwise, with that being said, I think I am done. Happy to take questions or dive into anything that you guys have.
All right. Thank you, Trey.